Yeah, good morning, participant. Good morning, all. Sorry for the delay that we will going to see for today's agenda. We will covering the EMI application using the CST Studio Suite. So we have this session that is been planned, and I'm thankful to the organizing team also that they have given us the opportunity to demonstrate our tool, which is the leading EMI tool for the RF simulation. And so, as you all know, the CST is basically a computer simulation technology tool, which is now a part of the Salt System Group, and that CST group will come under the similar project. And this is the same the Salt System Group uh, that delivers the Indian Air Force the Rafale aircraft. So that same group belongs. The CST also belongs to the same group. And for the today's agenda in our morning session, we will see how the different examples of the EMC simulation can be possible in electronic devices using the CST software. We'll go through the basics of the CST. As you all know, the CST has a wide range of different solvers, and we'll see their application in detail, and we'll explain what type of different solvers and what type of different machine technique that we are using, and what are the basics of the CST. And then we will go to the EMC simulation for the electronic device, as well as for the rule-based designing using the CST software. And in the next session, we're going to see different type of EMI capabilities of the CST software using on the PCB and some of the twisted cable pairs, as we have the simulation capability to do the interaction on the PCB as well as for the cables. So we'll see all this in our today's learning session. So the brief basic introduction about the CST, as you all know, the CST is the simulation leading tool for the RF industry. And as the CST is not limited to the antenna design, no, the CST has a wide range of application covering many of the designing concepts, including the automotive industry, some of the aerospace industry, the communication department, some of the defense organization, and many of the energy and healthcare devices. And the CST is basically a well-known, famous tool for designing, analyzing, and optimizing the performance of the electromagnetic compatibility. And we are also the leading tool for the EMI simulation. And our also our client portfolio comes from many of the different defense research lab, including the SEC, ISRO, and DRDOs, and many of the BEL and HAL defense organization. All those are using the CST tool for their different application. And many of the reputed institutes like the IITs and NITs are also the client of the CST software. And basically, the CST has a wide range of solvers, which covers the different spectrum from the very low frequency static application like the optical frequency, or it goes up to the multi-physics solver for the thermal and mechanical simulation. And for the particle effects, we have the particle in cell solver. So the CST has the wide range of availability of solvers, in which we have covered many of the application and many of the leading industries. And as I mentioned, the CST is not uh, the specialized tool for the antenna designing, but it also has the capability to do more than that. Uh, so the CST product and any of the end user of CST can be easily use the CST software to simulate many of the complex filters are there, couplers are there, many of the connectors, the RJ45 connector, the RF connectors, and many of the pin connectors. As It also covers the wide range of spectrum of different type of designing on antennas. Some of the PCB designings for the PCB rule check is there. PCB import export features are also been there in CSV software, and many of the waveguide simulation, many of the complex TWT structures, the photonic devices, some of the sensors, some of the actuators are there, some of the electrical machine for the low frequency. And the CST is also widely used for the SAR analysis, which comes in the biomedical application. Many of the end users are using the CST tool for the biomedical application, like the variable take, what are the SAR calculation, what are the human tissue absorption rate, and all those things can also be possible. We will see in today's session how from the basic to the advanced level, how the CST can be useful in different industry. In CST software, we offer the different type of CST products, and we have the different dedicated studios that is available. So in CST software, we have this flagship microwave studio, which will give you the option to do the designing of our RF simulation projects. Then we have the CST cable studio, in which we have the capability to simulate some of the cables and perform the EMI EMC on the twisted pairs or many of the straight single line cables or dual paired or different type of cables are available in the CST cable studio. We will see all the details in today's session. We have the CST PCB design studio, in which we can import or export the PCB from different vendors. We have the option and features to do the rule check, do the simulation of the PCB and perform the EMI EMC application on PCB using the CST PCB studio. The next is the CST design studio, in which we have the circuit simulation, which will allow the coupling of the 3D models with the symmetric circuitry design. And we will also see how this symmetric tool is useful for doing the parallel or the hybrid simulation. The next is the CST particle studio, in which we have the capability to simulate the EM fields or the freely moving charge particles in many of the closed cavity structures. The next is the CSTM Physics Studio, which will deal with the thermal and mechanical environment and how many of the environmental effects will happen are happening on the deformation of the structure on the EM fields. And last is the CSTM Studio, that's basically dedicated tool for the simulation of static or low frequency fields. So here we will see the different application of the different CST studio that we offer. And for the CST simulation, the first is the CST Micro Studio, which is the specialized tool for the fast and accurate 3D simulation of high frequency problems. Yes, and with the CST Micro Studio, we can have the capability to simulate the frequency selective surface, FSS structure. Many of the planar antennas are there, many of the circular horn antennas, many of the helix antenna. We have the capability to simulate the coaxial structures, many of the rectangular waveguides, and some of the planar devices as well. And also we have the capabilities to simulate the different type of filters. So the next is the CST EM Studio, which is basically a tool used for the design and analysis of the static or the low frequency structures. And its application includes the designing of the actuators, some of the barkers are there, some of the generators are there, some of the motors and sensors are there. And many of its application also covers the two coil simulation, the transformer simulation for the MQS frequency domain, some of the variable capacitors, some of the stroke magnets. Also, we have the capability to simulate the high voltage insulators, some of the port magnets are there, and the RJ45 connectors can also be simulated. The next is the CST Particle Studio, as the CST Particle Studio is a leading tool for the fast and accurate simulation of charge particle dynamics in the 3D EM fields, and it is basically suited for performing the task and for the designing and optimization of the magnetrons and some of the tuning electron tubes to be modeled on the particle source. And many of its application also includes the simulation of magnetrons, some of the traveling waveguide tubes, some of the coaxial connectors, some of the output cavity, the beam positioning monitors, the electron gun simulation, the multi-beam gun simulation, and many of the pierce type gun simulation can also be possible. The next studio is very useful tool for many of the defense industry, and they are using this studio for getting some of the analysis that's been performed on their electromagnetic or some of their RF devices. And this is the CSTM Physics Studio, and the Multiphysics Studio has the capability to do the analysis of thermal and mechanical structural deformation on any of the RF component. So basically, many of the defense industry or clients are using the M-Physics Studio for getting the environmental simulation in which they can simulate their RF component in the different atmosphere, and at the maximum peak atmosphere or the lowest temperature, they can have the environment that can be created into an EM simulation tool, and it will give the what are the deformation that is happening on the objects, and what are the structural deformation if it's the bending of the outer walls on the closed cavity structures are there, some of the cum-line filters are there, at what temperature the RF component will be able to be get simulated, and what are their deformation, and they can plot the frequency graph for the temperature versus frequency and all those things. So the M-Physics Studio is basically very handy tool for them, and for doing all those thermal and mechanical deformation and structural deformation problems. Uh, for many of the examples also include the induction cooker, many of the accelerometer, some of the cum-line filters are there, some of the thermal core simulation with the heat sink, and many of the circuit breakers. These are all the examples of the CSTM Physics Studio. The next is the CST Design Studio, as the CST Design Studio represents the universal platform for doing the circuit simulation and doing the basic combined circuit or the simulation of the entire complex structure using just the single 1D circuit block elements. We have to change, we have to take and select the circuit blocks that is available in the component library, and we can explore all those things. And for the doing the core simulation, we call them as the symmetric tab, which will be very useful for performing the application task and for designing the antenna matching circuit of the antenna and doing the optimization with the matching circuit. That can be possible with the help of CST Design Studio. The next example is the CST microstrip phase bridge, which will be connected and simulated using the single circuitry block elements. We just have to take the single circuitry blocks. We have to enter the values, define the materials, and we just have to do the connection. And using the 3D import layout structure, that structure can be created into the 3D format. The same way, we have created the hairpin microstrip filter, which is being simulated in the symmetric one. And as you can see, the different type of circuit to block elements has been used to create the hairpin microstrip filters. And many of the bending circuitry blocks are available in our component library. And we just have to give the values. And once the connection has been done, we have to simulate it. And that same thing can be, the single circuitry will be converted into the 3D layout structures. The next studio is the very important studio for the EMI EMC persons for doing the EMI EMC stuff. And the PCB designer studio that we have this specialized tool, which is useful for investigating the signal and power integrity and many of the simulation of EMI EMC effects on many of the printed circuit boards. And as you can see, this is main basic demonstration on how the PCB designing has been done using the CST PCB Studio and how the signal integrity analysis has been performed. Later on, we will also see how this CST PCB Designer Studio is useful tool, how we follow the basic steps and how any of the end user can perform simulation tasks using the CST software. The next studio is the CST Cable Studio, and as the name suggests, it's the specialized tool for doing the simulation of cables, and those cables which are the main heart rates of any of the system. As you take some of the automotive industry, any of the car industry, or any of the aerospace industry, the majority role has been played by the cables which will carry the signals from one system to the another system. So as the complete system, the main role for the cables is just like the veins in our body, take the main source from one point to the another. So basically in CST software, we have this dedicated cable studio, which will allow the end user to simulate different type of cables, which is being designed in our studio. They can perform the task for the different cables and many of the different type of cables, how we can go through the different type of simulation cables. And in the later session, in the later part, and using the CST Cable Studio, we have the flexibility to simulate the signal integrity or EMI EMC effects on the cable. And if it's the single pair or the twisted pair or any of the complex cable harnesses are there. And we have the capability to also simulate the cables along with the connectors and create some of bending angles at the specific location. We have all the access to do all those stuff, and we will see how the cable studio is very useful for simulating the cables later in later session. So here it completes the basics of some of the CST Studio that is being included in the CST software. Now we will see some of the add-on tools which has been very useful for the different application. And the first is the Antenna Maker software. And basically, the Antenna Maker software is very useful tool for the designing and modeling process of the different type of antennas. And yeah, the Antenna Maker software is the leading tool which has the database of more than 350 different type of antennas that has been pre-simulated and designed into a software. We just have to search for the different type of antenna and we can have the simulation, and the task has been performed with the less amount of hardware that is we have. So we'll see what is the main basic functions of the antenna maker software and how all this tool has been correlated with the CST simulation software studio. And with the help of the antenna makers, we will also going to see and take one of the live simulation example at the time of doing the cable simulation in the cable studio. We will also perform a task where we required a Wi-Fi antenna that's been connected with a twisted cable pair. And for doing all the simulation, we will see how the antenna maker software tool is useful for the end user. So let me open the antenna maker software for you guys, so you can get the basic idea and you can explore the main features of the antenna maker software. And here, as you can see, the antenna maker's home task is been there. So this is the main UI of the antenna maker software, and here it's just in the tabular format, as many of the end user is familiar with the Microsoft tabular format. The same tabular format structure has been used in the CST also. So from here, we have these three options that are available. The first one is the find antenna. The second one is in the array layout. We have the option and capabilities of the antenna maker software, which will give the end user to create some of the array structures in just few seconds, and they can perform and get the estimated task and the performance of the array with the lower amount of hardware that they can have. And as I have mentioned, the antenna maker software has more than 370 different type of antenna templates that has been simulated. We just have to use all those templates, and all those templates has been used and utilized for doing the further simulation within the CST software. So as here you can see in the template group, we have the different grouping options that are available. We have some of the simulation of the different type of antenna that has been used as the horn antenna. We have this all different type of fonts that has been designed. We just have to use these templates for doing the further simulation. And we will also see how this different type of antenna templates can be useful for the designing part. All those antenna template is pre-designed. We just have to use this template and do the simulation, and we can also create the antenna with the variables, and we can also play with the different simulation tab in which we can change some of the variables, and we can also estimate the performance and the degradation and the upgradation of the antenna performance. So here are some of the planar antennas that we have in the antenna maker software. And here are some of the templates that we offer for the wire antenna. These are some of the array templates which will be very useful for the 5G MIMO application. And we will also see how the CST Studio helps the end user to create their task for creation of the 5G MIMO antenna under sub-6 gigahertz or 28 gigahertz range. We will also have the different dedication for all those end users who are working on 5G. So we have all those updates that's been regularly coming for the different type of end users. So from here, we have all these antenna templates, and from here you can search according to your keywords. Suppose if we are interested in getting the 5G antenna, we search for the 5G and it will display the antenna templates. which can be a useful container for the 5G application. Yeah, here you can see more than 14 inbuilt templates are being useful for the 5G application. We'll see this wave series feed rectangular microstrip patch, and from here we just have to download this. It's been just downloaded in just few seconds. And from here, you can explore what are the different antenna templates, what are their frequency bands, some of their radiation patterns. So this is the main overview of this selected antenna. And you can get the sketch of this antenna, and you can have some of the design guidelines, or you can also view the model which is being simulated. And from here, you select the sketch option, and you can get the exact dimension, what are the dimension of the antenna. And in just few seconds, as you see, I just have designed and done the simulation part and done the estimate performance of this antenna. So this is the main sketch. This is from the top view. What are the dimensions the designer of this antenna has taken? And from here, you can get the model preview in 3D format. And from the next step, you can get the information, what type of this traveling wave series feed rectangular microstrip patch array is been there. This is the main documentation that you can have. You can go through what are the feeding techniques, what are the operational mechanisms, some of the impedance charts, some of the gain. So all the necessary document is been available in this format in the information tab. You can download in PDF format as well. And for the value comparison, we have this option and the tool in which you can compare the different type of antenna templates. And now we are going to see what are the performance graph plot for this antenna. And here you can see this antenna array has giving us many of the peaks on 2.5 gigahertz, some of the 2.575, and some of the 2.67 gigahertz. And we will see what is its VSWR ratio. And we can also explore its far field patterns and some of the gains. And here you can see the gain of the antenna. It's the total gain, and we can also have this in horizontal or LHCP gain or RHCP gain, and we can have the vertical gain as well. So this tool is much useful for the antenna person. They doesn't have to do the manual stuff of creating and modeling the different type of antenna according to their application. So this tool can be useful. They just use this inbuilt different type of templates, and they can play with their required simulation. Their according to their required application, they can play on, and they can use this tool. And as this antenna template, now we'll take this antenna model into the CST Studio Suite for further simulation. And from here, we have this export model option that is available. And from here, we export the model. The next is the export and open model. And the third is the export to the CST component library. And here you can see we can name this as antenna megas template 1. Yeah, and it's done. So now we will open the CST software. Yeah. And here in the component library, you can find this antenna template, which we have created and done the simulation in the antenna maker software. Yeah, here it is. So as here you can see the same antenna with all those parameters has been imported into the CST Studio suite, and we can play with different type of application, and we can recreate the structure using the CST tool. So by this, the antenna maker software is much useful for doing the task for many of the antenna simulation. So this is the main features of the antenna maker software that we offer. And for any of the defined frequency or any of the keywords, we can go with the MIMO application, or we can search for the Wi-Fi, and we can have the automotive antennas, or the coplanar antennas are there, or we can go with the lens antenna, or many of the stuff. We have the wide range of availability of different antenna templates in the antenna maker software, and for many of the applications also. So as I have mentioned here, from here you can have this different selection of the antenna maker software for the different specifications. As here you can see, so for the aeronautical application, for the airborne, or for the base station, we have this different type of VHF communication. Aerospace industry antennas are there. For the automotive industry, we have this long range radar communication systems are there. Some of the medium range, some of the short range, and some of the antenna that's been used for the remote keyless entry in many of the different environments, for many of the application covering the tire pressure monitoring systems and vehicle to vehicle communication, and all those different type of antenna templates that we have in the antenna maker software. The next is the device, for the base simulation, for the base communication, for the base station communication. Then we have the simulation for the UHF frequency bands, or for the wireless, or for the cellular devices, or for the WiMAX, or for personal area networks, and all these different type of antenna templates that we offer for many of the different applications. So by this, this is the main basics of the antenna maker software. And from here, and in the help and getting started, you can learn some of the topics, and you can also go with this video tutorial that is available. And by this video tutorial, you can also explore and get some of the basic information about the software tools that we offer. The next is the main thing about the library. So for the different applications, we have also the simulation task which has been performed for many of the different application covering the substrate materials. And in the antenna maker software, we have this option for the different libraries that are available, and we have the capability to explore what are the different libraries in substrate material, what are the waveguides, many of the connectors are there, some of the radom applications are there. So from here in the inbuilt library, you can select and go with the different type of substrate material that we offer. And here you can see search for the manufacturers from different vendors, like the Rogers are there, like the Teconics are there. So you can search for the different application of the vendors, and you can have this all this different type of substrate material covering the relative permittivity, some of the tangent, some of the substrate height, some of the copper height, and all those. And you can play with the different substrate materials as well. If the substrate material is not available in the library, then you can go with the creation of new substrate material into the antenna maker software. And the same way, the antenna maker software can also be useful for the creation of different type of waveguide structures also. And all the structure has been used into the CST Studio suite for performing the co-simulation projects. So here in the waveguide component library, we offer this different type of shapes of the waveguides that can be simulated. The first is the rectangular waveguide, the second is the circular waveguide, the third is the single digit waveguide, the next is double digit waveguide, and the last is the elliptical waves. So from here you can see the dimensions of this waveguide, and for the different frequency and for the different application, the waveguide dimensions are also there. We can select the different waveguide that is been simulated for different frequency. Suppose we select this 5 gigahertz frequency and just double click on it. As the name suggests, it's double digit waveguide. We go with the save option. And from here, we select this 5 gigahertz and we do the export model. And here you can see and visualize this waveguide that's been having all these parameters. And into the CST Studio suite, we can export this waveguide and open this structure. And we can save it into the CST format. Yeah, here you can see this waveguide for 5 gigahertz frequency range. It's been just created in simple structures and the format in few simple steps. We can have this capability and the option tool. Same way, using the antenna maker software, we can also give the end user the flexibility to design some of the connectors and some of the connector pins also. So in this library, we have the different options for the connectors. And from here, the end user can also select the different shape of connectors like the MCX, the MMCX, the N-type, the SMA, some of the SMPA, some of the TNC, and some of the UFL. And from here, we have these two category options that are available. The connectors sort out by the 50 ohm impedance, and the connectors for the 75 impedance are also there. And we have this selection tab that is our option available. And suppose we can take one of the example. We'll take this SMA connector, which has been designed for 50 ohm, and this SMA connector has the capability to perform the simulation for the minimum frequency range of 500 megahertz, and for the maximum it goes up to 40 gigahertz. So by selecting this, we have this option that is available, and from here you can name this as the 50 ohm standard connected, and as the minimum maximum frequency we have given. And as you all know, the coaxial connector, the SMP connector, we have the coaxial inner dimensions are there, some of the coaxial outer dimensions are there, and all the elements and what are the basis of the uh, connector, like the connection inner dimension diameters are there, connection outer diameters are there, and some of the pin extrusions are there, some of the connecting pin diameters are there. We, and for the relative permeability, we save this, and from here we do the same thing. We select this, export the model, and we can use the antenna maker software tool for creation of the connectors. And from here you can see the two models are option are available. The first one is the straight plug PCB mount, and the second one is the straight jacket bullet adapter. So both these options are available. So we are going with the first one, the straight plug PCB mount, and we just export and open the model. And from here, we just name this as connector SMA, and this connector of the SMA will be open in the CST Studio Suite. Just few more. Yeah, it's done. So from here, to get this working plane, we check this axis boundary. And as you can see, the connector pin has been imported into the CST. You can visualize this. This is the connector, and we have all the specification that has been designed. This is the coaxial casting. This is the dielectric. These are the 4 foods that we offer for the connection. And these are the 4 legs. And this is the pin that we have connected. And this is the main sphere and the square base that we have. So by this way, using the antenna maker software, we have the capability to use all these features that's been co-simulated into the CST Studio Suite. So by this, the antenna maker software has the option to for the end user to also create the connectors as well. And by this, we have seen the substrate material. We have gone through the waveguide simulation or performed the waveguide with the help of antenna makers. Then we have also done the simulation for the connectors as well. And the last but not the least is for the simulation of radomes. So many of the end users are working with the radome simulation, and we have this different shapes of the radome that we offer. And here we have these different shapes, and for these different shapes we can have the simulation that can be easily possible. We will select this conical spherical blunted radome, and same way we do the export model into the CST, and we do this as export, and we just name this as a radome example. And here you can see the radome example has been opened into the CST Studio suite. Yeah, here it is. So here you can see this complex design shape can also be created in just few clicks, and with the help of antenna maker software also you can play with the different type of simulation like that we have seen today. So by this, we have covered mainly the specification and the option tool of the antenna maker software. And the last is the toolbox. And for the toolbox, we have these different options like the data conversion for the chart tracer, for the angle, for the length. Some of the inbuilt calculators are there for the phase transmission equation, or you can go with the radar range equation, or you can calculate the signal to noise ratio, or you can go with the system temperature calculation, or for the communication downlink equation. You just have all these inbuilt calculators which will do the mathematical work for you. The next is the antenna properties, and in the antenna properties we have the conversation for the gain to the beam width. We have the conversation for the gain from an aperture. We can calculate the antenna efficiency, the radiation efficiency, the antenna temperature, or the realized gain, and many of the things. And we have this transmission line calculator, which will give you the exact calculation for doing the transmission line that can be performed on the microstrip patch. And we have this microstrip line calculator. We have the coaxial cable simulation uh, line cable coaxial cable connectors calculation are there. If you are interested in doing the coplanar waveguide calculation or the circular or rectangular waveguide calculation, we have all these different type of calculators are available, which will do the mathematical work for you. So here we have gone through the basics of Antenna Maker Studio software. And here some of the steps that we have taken for the 5G MIMO antenna, and all these antenna templates are much contender for the upcoming 5G MIMO applications. The next software or the next add-on tool is the Filter Designer 3D, and this tool is very much useful for doing the simulation for the complex or the band pass filter or the diplexers, or for the filter designing, or many of the cross coupling, and using all those advanced topologies we can have the capability to simulate all those structures, the heavily matched structures for the filters. And using the Filter Designer 3D tool, we have this option to perform the simulation task in just very in very few simulation time is required. And using the different methodology like the individual single circuitry blocks, the three along with their connection in between which we have placed the tuning screws are there, and we have changed the scattering parameters of the filters, and we have also done the filter optimization and tuning as well. So this tool is basically used for the band pass or the diplex or filter designing part. The next tool is the Spark 3D tool, which is a flagship tool widely used by many of our defense lab in our defense, many of our defense laboratories. And this tool is much useful for giving you the accurate results on RF breakdown, and for the RF breakdown power level simulation. We can have the capability to perform the simulation task for the passive devices, which includes closed cavity structures, the waveguides or antennas. So basically, the Spark 3D tool is useful for giving you the simulation result at the different breakdown level, which covers the breakdown with respect to the vacuum or gas discharge. So basically, this two multiplication breakdown analysis has been performed by many of our defense lab, in which they have designed any of the components like the cavity structures, like the antennas or the filters, and all those cavity structures and all those RF equipment has been sent into the outer space. And in the outer space, the environmental temperature, many of the conditions are there, like some of the presence of the atmospheric gases are there. The temperature are bit very low or bit very high into the outer atmosphere. So by in the simulation, in the EM simulation software, we have using the Spark 3D tool, we have given this capability to create all those outer atmosphere environment into the EM simulation project, and they have created and used the Spark 3D tool for creating the vacuum breakdown analysis as well. So there, in this Spark 3D tool, they have created the environment in which they can simulate and perform the tasks of their closed cavity structures, and with the presence of different gases, they can simulate. They can create the environment with the different availability of gases like the helium gas, the hydrogen gas, the nitrogen gas, some of the peroxide gases are there, some of the air vacuums are there. So using all these environmental studies and all these tasks, they can perform and see what are the degradation that is happening into their design structures or into their cavities or into their band pass filters are there that they have created. So this tool is basically useful for the RF breakdown analysis. The next tool is basically also a very handy tool for doing the band pass simulation in the dual mode. If it's the designing of dual band pass filter or dual mode filter or low pass filter, and as you can see, designing all these complex structures and modeling all this structure is a very difficult task for any of the RF designer. So using the Phase 3D tool that we offer, they can just drag and drop the single circuit components, and this software use the mode matching methods in which they can compute this heavily meshed created structures like the waveguides or the coaxial cavity structures in just small simulation time, and they can have this accurate result, and they can also do the synthesizing tool, synthesize and optimize all these structures as well. So now we'll see what are the new major upgrades that has been added into the CST's latest version. And as in a recent trend as in 2021, for in the RF domain, the trending topic is 5G, and for the 5G capabilities, the CST software is capable of giving the end user to create all those 5G environment. And here in the latest version of the CST 2021, we have created and designed the CST 5G phone, which has been equipped with 3mm wave antenna array for the 28 gigahertz frequency range. And they focus for giving you the most coverage and giving you the best coverage in all the directions. So from here we will see, and we can also do the simultaneously explore the main key features of the CST software as well. So just uh, I will close all those old projects, and we can start with the new project template. And from here, we just start the CST Studio Suite. And here you can see the main first home page of the CST Studio Suite software. And here you can see we have this component library option is available. So in the component library, we offer more than 200 plus inbuilt design components for the different applications. So all these components has been pre-designed and placed into the CST. The end user doesn't have to recreate all those structures. They just use and download all these structures. And from here, in the component library, we have created and added the 5G enabled smartphone that's been integrated with all those components. Just few minutes. Yeah, here here it is. So as you can see, this is the design smartphone for the 5G application, for the 5G coverage area. And from here in the component library, you can have and explore all these different uh, components of the smartphone. Here is the antenna. Here you can see the phased array antenna has been placed. This is the 2x2 array. This is the 4x1 array. This is the main Wi-Fi antenna. This is the Bluetooth antenna, and many of the planar antenna has been integrated. And as you can see, we have all these different type of antenna templates that is being available for the simulation. And here you can see the 5G antenna has been implanted. That's an array in the array format they have created. The next is the CMA antenna. That's basically a planar antenna that we call. And these two are the Wi-Fi antenna that has been implemented, has been designed into the CST smartphone, CST 5G smartphone. So from here, you can explore and play with the component library options. This is the battery. This is the battery. This is the main camera. These are the connectors. These are the housing, and this is the main PCB, and this is the main home screen. So here you just have the option, and you can play with the inbuilt components that are available. So here, as you can see, we have more than 480 plus design components that are available in our component library. We just have to select, or we just have to use any of these components, and from here you can search for the patch, and you can see all this different type of patch has been created and designed for the end user. You just have to use this and download this. Yeah. So from here you can have visualization how this patch is performing, and it's giving around 1.6 gigahertz, around minus 28 return loss as parameter we can explore. So by this, the component in the component library, you can explore the different type of projects that is available, and you can use them for further simulation into the CST Studio Suite. The next thing is the 5G antenna design template, which is available in our latest version of the CST software. And from here, we have the different project templates. I will demonstrate what are these project templates and how the end user can explore the different applications. But here in the antenna, we have this two dedicated 5G project template that has been added into our latest version of the CST software. So just let me open that project template for you. From here, new and recent is there. And from here, you can click on this new project template. And here we have this microwave and RF optical project template. And into the antennas, we have these two created, we have added these two new project templates, which is dedicated for the 5G application. The first is the mobile device simulation for the sub-6 gigahertz frequency range, which is widely used in our Indian country for the development of 5G and for the smartphones or wearable techs. And the next is the 5G millimeter wave application. So these two new project template has been added into our latest version of CST 2021. So by the project template, I will explain what are the project templates. So basically in the CST, we offer doing the simulation in this 5 different domains. And the first one is the microwave and RF optical. The second domain is for the EDA electronics. The third one is for the EMI EMC domain. The fourth one is for the particle dynamics. And the fifth one is for the static or low frequency application. So if the end user is not much familiar with what type of solver that they have to select for their application, they can just go with the project template, and using this project template, they can be they have given the suggestion to select the best appropriate solver according to their application. So we will see these different project templates and what are their tasks. First is the microwave and RF optical. The first one is the antennas. In antennas, we offer the simulation of waveguide, some of the planar antennas, some of the wire antennas are there, some of the phase array for the 5G MIMO application, some of the dielectric resonators are there, some of the reflector antennas like the reflector dish or the reflector horns are there, and the next is the RFID tag. So these are the different areas for the antennas. For the circuit, we have the option for the waveguide and cavity filters, some of the planar filters, some of the couplers and dividers, some of the packages, some of the multi-pin unshield connectors are there, and many of them are coaxial connectors. So the next project template is dedicated for the RCS calculation, and in the CST, we have this tool and we have all this option for the RCS calculation. First is monostatic or bistatic. Some of the ISAR simulation can also be possible, and multi-static or the RCS with the material features and the radar range profile or the time signal radars are also there. The next project template is dedicated for biomedical or the exposure of the SAR analysis. So for the biomedical application, we have this project template for the calculation and doing the MRI simulation. And the next is the exposure of the SAR. We'll also see how the basic functions of the CST software in biomedical and for the SAR as well. The next is the optical application, which covers the plasmonic and the dielectric structures. And the last is the periodic structure, which will cover the FSS structure with the unit cell or the full structure as well. Now we change our domain to the ADA and the electronics. And here in the ADA and the electronics, you can find this many options and tools. First is signal integrity analysis. The second one is the power integrity analysis. The third one is SIPI co-simulation. The fourth one is broadband model extraction. The fifth one is narrow model extraction. And the last is the design rule check. In the signal integrity analysis, that's the SI analysis, we can perform the parallel interface or the series interface. And as you just go with the parallel interface, the software will automatically recommend the user the best suited solver for their application. So here, as you can see, we are in parallel interface. It's suggesting the end user to select and go with the PCB transient solver, which is best suited for parallel interface and performing the signal integrity analysis. And as we are in the antenna and we are going for the 5G, it's showing us the time domain transient solver. So using this project template, the end user can have, the software can guide them the best suited solver according to their application. So the next is the power integrity analysis. The power integrity analysis, we have these three options. First one is the DC-IR drop analysis. The second is the AC impedance analysis. And the third one is the decap optimization. The third workflow that we offer is the SI and PI co-simulation. So the end user can perform the signal integrity and power integrity in the same domain. So the SIPA co-simulation, we have this frequency domain solver that's been best suited for the end user. The next is the broadband model extraction. And for the broadband model extraction, we have these different options. We can go with the simulation for the package. We can also simulate for the PCBs. We can go with the connectors or the chips or the cables. And according to their selection, the best suited solver has been recommended. The same thing will happen for the narrowband model extraction. And model, we can have and simulation that's been performed by the PCB, package, connectors, and chips. And the last one is the design rule check. In the design rule check, we have this PCB rule check option that is available, in which any of the end users can check if the PCB is completely printed or designed or not. And if any of the end user can have in that those design PCB, if there are some of the connection pins, the mismatch or the connectors or the the signal carrying lines are being distorted or been misplaced, they can go with this PCB design rule check. The next domain is the EMI/EMC domain, which is basically much useful for our today's session. And for in the EMI/EMC domain, we have this option to perform the radiated emission, the conducted emission, the conducted susceptibility. The next is the radiated susceptibility. For the components, if the end user is interested in performing the EMI/EMC on components, they can do that. And in the EMI/EMC, we can also offer the PCB rule checking as well. So we will see in the radiated emission, we have these three options that are available. The first one is the high speed signal. The second one is for the power electronics. And for the third, we have these cables. So the RE can be performed for the following three. Now we will see the conducted emission. The CE can be performed on the bus bar, on the PCBs, and on the cables as well. The third is the conducted susceptibility, that CS we call them. And for the CS, we have the selection for the EST, for the lightning, and for the BCI. The next is the radiated susceptibility, that's the RS. And for the RS, we have these four options. We have this HIRF, that's the EMP, and for the electronics and for the interface as well. Uh, the last second is the component, and for the components, for the EMI, EMC on the components, we can check the shielding efficiency of the enclosure. We can go with the EMC filters. We can have the common mode chocks. We can perform it on connectors, cables, and PCB. And for the PCB, we have these two options. That's first one is the rule checking, and the second one is the 3D simulation. And as you have selected the 3D simulation, it will suggest you the best solver for your application. And the last one is the PCB rule check. That's a very handy tool for the PCB simulation. The next domain is for the particle dynamics, and it covers the accelerator components, some of the vacuum electronics, some of the space application, and many of the beam optics are there. And the last domain is the static low frequency, in which you can have the simulation task that's been performed for the electromagnetical devices. Some of the high voltage currents are there, some of the magnetic designs are there, some of the sensor simulations are there. And here we have this option for the EMC shielding as well. And in this EMC shielding, you can find the cabinet and housing tasks are there. And by this, the CST suggests us to go with the low frequency domain solver, which is best suited for your application. So by this selection of the project template and according to the different application, the best suited solver of the CST is being offered to the end user. The next 5G, the next update for the 5G in the CST's latest version is we have this capability to perform the post-processing tab, the post-processing simulation for the 5G with the help of the code book concept. As much end users are as many of the end users are familiar with the code book concept. Basically, it's an written text format in which the end user can mention their codes, and the software, the EM simulation software, will read and process all those codes, and they can perform the task for doing and giving you the post-processing results. And for the 5G tab, for giving you the 5G millimeter wave simulation for the performance output, we now support the code book concepts as well. And the last update that comes in the biomedical biomodel is we have the wide range of different availability of biomodels that are available into the CST. So basically, a biomodel is a human body created simulation objects in which, with the help of in the EM simulation software, with the help of all these biomodels, the end user can perform the SAR analysis. They can perform many of the different holding grips of the cell phone or the smartphone, or they can go with the simulation of the 5G enabled phone containing all those array, and they can calculate the SAR analysis as well. So in the CST's latest latest version, we have included all these biomodel updates, into our software. And here you can see we have these different holding hand grips that are available. And from here, you can search for the biomodels and you can visualize and get the idea. Here you can see we have simulated the SAR for the head and hand along with the smartphone, the 5G enabled smartphone. Yeah. So from here, many of the end users who are working on wearable tech or for the biomedical application, they have a very useful tool that's the CSD software, in which we offer the simulation of the human head along with the human body as well. So let me explain what are the different type of biomodels that we offer into the CST. So for that, we are selecting the blend template. Yeah, the blank template has been opened, and from the modeling tab, we have this import and export features are available. And from here, you can select and go with the 3D files. And here you can see the voxel data is there. So from the voxel data family, we have the different options. We have these different models of the human body that has been created. So the first one is the baby tissue. Yeah, sorry for the delay. My connection got lost. So here I am saying we have this different biomodels option that are available. So here we have these different options, like the first one is the baby, the second one is the child, which is around 4 years, and we have these two models, the human models of the men and women both. So from here you can select the baby, and from the selected biomodel for the baby, we can have the preview for it. And using this biomodel, we are going to have all the inner components of inner body parts, like the kidneys are there, some of the livers are there, and their muscles, their fats, their veins, their brains, and all those things. So from here, by selecting the specific area or the specific range, we can select and go with the biomodel simulation. So if the end user are interested in simulating the only the head, they can select the head portion only, and all those head portion components has been used. and they just pressed OK. Yeah, here it is. So from this can get the idea of the human head, and from here you can see this is the bone, this is the brain of the baby, these are the eyelids, this is the fat, this is the muscles, and this is the skin. So by this manual selection, the end user can perform some of the simulation tasks like the SIR calculation and all those things. And from using all these biomodels, many of our leading industry, our client from the biomedical, in working in many of the biomedical application, in many of the wearable tech, they are using our CST tool for performing all those simulation according to their applications. So the next thing that we are going to focus is the selection of the solver. As you all know, the CST has the wide range of solvers and the availability of solvers for the different application. So we'll see what are the basic solvers and how all those solvers and what are its application. So before starting and selecting the appropriate solver for your task, I will suggest to go with the following parameters, which will also play a very important role for giving you the best output from any of the EM simulation software. So by selection of the solver, no doubt that's the main task, that's a main key option for the selection. But the solver, before selecting the solver, all the following parameters will also play a major role for giving you the best output from any of the EM simulation software. So many of the end users, many of our end users are asking us what are the best appropriate solver for their application. Some of the solvers are they have done and they have compared, like for the basic microstrip patch, they have done the simulation in time domain solvers as well, and they have simulated the same structure in frequency domain solver. But in both the solvers, they are getting a bit comparison. They are comparing the results of both the solvers, and they are getting a bit of variation with the same design that's been performed with the same parameters. So we always suggest our end users and we always tell them the selection of solver is also a key important role for giving you the best output from any of the EM simulation. But along with the solver, there are few parameters which will also play an important role for giving you the accurate result. So the first parameter is the electrical size. The electrical size means the geometry of the object that you have created in EM simulation software tool. So how big is your how big is your model in the electrical size? That also plays an important role, giving you the best and accurate results. The second one is the material models, the material properties that you have selected. What type of material that you have used? What is the properties of the material that you have used for creating all those models will also play an important role in giving you the best output. The third one is the resonant behavior. So resonant behavior means what type of different feeding technique that you have used. Like if you have used the coaxial feeding, the prop feeding, the microstrip line feeding, what type of resonant behavior you have used and what type of feeding technique that you are using will also play an important role. The fourth thing is the type of meshing. So in the EM simulation software, just like the CST, we have the option to select the we have given the different type of meshing availability options are there. We will see what are the types of meshing and how the meshing is important in next few slides. So what type of meshing you have selected for doing the simulation? That also plays a major role for giving you the best output results. And the last is the boundary condition. What type of boundary condition or the environment that you selected to perform the simulation from the EM simulation software. So all these parameters will also play a major role giving you the best output from the CST software. And the last is the some of the acceleration methods that we offer. So the different type of acceleration methods that we have, and the CST solver has the capability to boost your simulation with the availability of hardware. So different type of supported graphic cards are there. Some of the boosting of the GPUs are there in many of the workstation, or higher core multiprocessors are there. Though, so using all these acceleration methods, the CST tool is capable for giving you the boost in your simulation as well. So all these parameters will also play an important role for giving you the best output result from the EM simulation software, just like the CST. Now we will come again back to the selection of solver. Yeah, so we have these two general purpose solver. The first is the transient and the time domain solver, we call it. And the transient solver is basically used for the electrical medium or large size structure problems. We can have the simulation that's been performed for the broadband analysis as well. The second is the frequency domain solver, which we have, which is very useful for the narrowband or the single band operational frequency. And basically for very electrically small to medium sized problem, the frequency domain solver is best suited for your application. And many of the periodic structures, like many of the layered periodic structures like the random simulation or multi-layer co-PCB simulation with the floquet boundary modes are there. The frequency domain solver is best suited in that task. There are some special solvers that we offer into the CST. In CST, we have around total 18 different solvers covering different applications. So we just have we are just going through some of the basic and well-known and must-use solver for our applications. The eigenmode solver, which is basically used for the closed resonant cavity structures like the simulation of cavity, bending elements, bands, coplanar waveguide structures, filters, simulations are there. The next is the integral equation solver, which is basically a very useful solver for very electrically large size structures. So electrically large size structure means the dimension of the structures are very large, like the aircraft simulation, like the simulation of any of the automotive car, which is having length in many of the meters as well, or the simulation of the ships are there. So all these heavily electrically large size structure have different type of metal has been used for creation of all those models. So integral equation solver is best suited for all those simulation having the electrically large size structures. The next is the asymptotic solver, which is basically a solver dedicated for the RCS calculation for many of the electrically large and very large structure containing the RCS simulation can be possible. And the last is multi-layer solver. As its name suggests, this give you the end user the access to create and simulate the layer background structures like the multi-layer PCBs are there. So these are the basics of the solver that we offer in CST. Now we will see what are the different type of machine that we have, and what type of different type of machines that we can select into the CST Studio Suite. So in the transient, in the time domain solver, we offer this hexahedral machine, as here you can see in the first picture, this one. The second one in the frequency domain solver, and for the eigen mode simulation solvers, we have this tetrahedral machine, as you can see here. And for the integral equation solver, that's basically very useful for the electrically large size structures. We have this surface meshing over here. So basically a well meshed object or the model is must being useful for the end user to give the accurate output from the CST Studio Suite. So if the structure is less meshed structure, some of the corners or some of the parts has been neglected by the EM simulation software. So the EM simulation software just calculates all those structures that is being meshed. If the structure is not meshed, that part will be a bit neglected, and that will create some type of simulation loss in your output. So we suggest the structure should be heavily or properly meshed, by which the EM simulation can perform all those mathematical algorithms with the selection of different solvers that we have, and it can give you the accurate and the best result from the CST software. In the CST, we offer the end user to change the type of meshing according to their requirement. So here in the meshing property, we have the selection of the different type of meshing, and the end user can change the meshing settings as well. So the next is getting started tutorials, and from the CST we have this very good and helpful getting started tutorial are available. So in this help menu, you can find the PDF format of all the different CST Studio that we have seen earlier in today's session, and you can find the PDF format of the books that we have created. And so you can go into the help setting. Just let me take you to there. And from here, you can see in the help, there is this getting started books. Getting started books are there. You can just click on that, and you can see this getting started books are there. You can go with the PDF format. That's all these different studio books are available in PDF format, and you can explore some of the inbuilt examples that we offer, and some of the hands-on trainings are there. The next is the getting started videos, and in the getting started video, you can find you can see and have the visualization that is available. So here in this getting started video, we have these two basic video which will take the end user to the basic modeling, and for in this 38-minute video, it will take you to the advanced modeling tool and what are the basic operational tools that we have. So by just clicking this, the getting started video tutorial has been started, and you can go with the simulation and how you can create and design the basic antennas and how you can perform the task. And here in the advanced getting started video, you can have the visualization about the basic modeling that we have offered. So from here, you can explore this. So these are the different shapes that are available for the creation in CST. So by this, you can get the idea and you can go through the different modeling and simulation. So here by this, you can change and degrade and scale the simulation. You can perform the Boolean task. You can also do the further simulation. You can twist the objects. You can loft the objects as well. You can go through the performing of simulation on different projects as well. And by using this single 1D curve, you can change it into the different formats. So here in the getting started tutorials we offer, we have this very useful tool, that's the CST software that comes with all the help documentation that is being required. And here we have gone through the component library. Just I will explain what are the component libraries and what are the tools and models that has been pre-designed. And from here, we have also searched for the antennas and all those things. So in the CST software, when there is always in any of the dialog box, if you always find this help button is there. So according to the dialog box pop-up, the help option is there. And this is the basic example. If the end user is not much familiar with the selection or the what type of accuracy that he or she has to select in the time domain solver, they can just click on this help, and the help documentation regarding this pop-up will be shown to the end user. So they can just go through that information and they can perform the task. So the next is the basic EM simulation workflow, and it starts with the idea or the concept. We have this basic idea or the concept that is there, and with that idea and concept, we are using any of the EM simulation software or the tools. And here the EM simulation software tool plays a very important role. Using the CST software, you can create the virtual prototype or the model of the device. Then you can perform the numerical methods or the solvers selection. With you can create the calculation, do the simulation with different numerical techniques. Then we have the analysis of the results, and then we have this prototype measurement, and we can go with the final product results. Sorry. So as this is the main user interface of CST Studio Suite, let me take you to that into the CST software. Yeah, here is the main user interface of the CST software. And here you can see this is the main primary window where we are going to simulate and design our structures. From here, we have the selection option for the units that we have. And for the dimensions, we are selecting with the millimeters, and for the frequency, we are selecting as gigahertz. This is the main primary window that in which we can create the modeling. And here is the tabular format, as much end users are much familiar with. That's the same Microsoft format, the tabular format. In the same format, the CST software has been offered. So in the main home taskbar, you can find the units options are there. The selection of the solver, you can have the different selection of solver according to your needs. We can have the start simulation object button is there. Then we have this meshing properties, and we can visualize the structure in mesh. We can have the visualization of structure in mesh view. We have this meshing settings are there, and we have this macro tool that is available. We will just see in just next few minutes, we'll see how this macro tool is useful in designing part as well. The next is the modeling tab, and from the EM simulation software, from the EM simulation workflow, the first of all, we require to do the modeling. So in the modeling tab, we have all the options that is useful for creating and creation of the models. The second is after modeling, we are interested in doing the simulation part. So we are dealing with this simulation tab in which we have to define the minimum maximum frequency. We can change the boundary condition settings are from here. Different type of source and the feeding mechanisms are there. We offer the waveguide port. We can have the discrete port with discrete port to the wire. We offer the plane wave. We have this lumped element ports for the wires and many of the things. And in the simulation part, we have the tab for the field monitors. And for the field monitors, it's the result monitors that we are interested in seeing this after the simulation will be performed. And once the simulation has been done, we have this post-processing tab. And from here, you can find all those post-processing results. And we also have this result template, which is being useful for creation of the custom 3D results, custom results, according to the user's requirement. And the last one is the viewing options that are available. So from the modeling, you can explore some of the basic modelings and tools. So here in the material section, in this material tab, you can find the material library. And in CST, we have the wide range of different materials that has been created, and we have different type of materials that is available. So here we go with the copper. So as you can see, their main properties and options has been listed down. You can just use all those materials. You can have this iron, you can have the air, you can have the vacuum, you can have the steel. Yeah, and many of the sorry, many of the FR material, FR4, or many of the things, you can explore this. And using the material library, you can define the material to the models. If any of the material is not available into the material library, you can create your own material from this new material tab option is available. And here you can define the problem type. Sorry. And from here you can define the epsilon, the mu. You can also define the conductivity, some of the dispersion, the thermal properties, the mechanical properties, and you can define your own custom material, which has been added to the material library for your further simulation. So in the modeling tab, So in the modeling tab, we have this different basic models and options for creation of models. And here you can see in visualization in the 3D format. Sorry. So by this, using the different modeling tools in the CST, you can have this option to create your custom design models. And sorry, if you are not much familiar what are the dimensions, so from here you can have the visualization of the dimensions as well that you have created for the model. You just head towards the view option, and here in the view option you can find that add dimensions. You can add the distance dimension. You can select any of the dimensions that you are interested in. And just by double click, you can have the idea that these are the dimensions for the object that we have created.
Abhishek, can we go on a break or something?
Yes, ma'am. Hello.
Yeah.
Yes, ma'am. Please tell me.
Can we have a break in between so that I think you can also take some sound rest?
Yeah. Yes, ma'am. Ma'am, tell me at what time we can resume?
It can be a lunch break, I guess. As we had discussed, 2 o'clock is what we had decided, right?
Yeah. Okay, fine. Not an issue, ma'am.
Videos to show in between. You wanted to? We have already shared it with the in the WhatsApp group.
Okay. Yeah. Ma'am, just we can continue for half an hour, ma'am. We can go on break from 12:30 onwards because some of the basic concepts I just have to demonstrate in the morning
Yeah,
session,
sure.
and in the evening session from 2 to 4:30, I can go on. We can deal with all the EMI EMC stuff using the CST.
Okay, sure. Because I thought since
Yeah.
we've been talking for such a long time,
Yeah. Not an issue, ma'am. It's my not an issue from my side. I've gone through many of this session, like this session. Not an issue. We can continue, ma'am.
Yeah, thank you. Please.
Yeah. So as I mentioned, you can go and play with the dimension selections as well. So this is the main UI of the CST Studio Suite. And one more thing that I have to cover is in the macros, we have the different options for the creation in macros. So again, let me open the basic template for you. Yeah, here it is. And from the macros, you can have the different construction of the different models and the materials as well. So from here in the macros, we have this horn antenna. We can select the horn antenna as well. And as you can see, the CST software automatically calculates and create the horn antenna for the different application, for the dedicated application. So in the macros, we have this construct options are available. You can construct many of the coils, many of the demo examples like the dipole antenna or the EMI EMC box are there, microstrip filters, many of the horn hairpin filters, the waveguide with the T-steppers are there. You can design and construct all these things. The next thing is in the macros, we have the option to calculate the port excitation coefficient. We can construct the microstrip coefficient for microstrip lines as well. And here from the inbuilt calculator, we can also calculate the simulation for the ports. And using the different options that are available in macros, you can calculate the port excitation or you can create some of the biological tissue properties or the human model properties as well. So the project template that we have already seen, and some of the standard results that are being visible into the CST software. The first is, this is the basic 1D result or the 1D graph plot that is being available. So this is the main 1D graph plot in the tabular format. This is the 2D and the 3D result graph plots. And this is the realized gain for the far field result that we offer. And from here, this is the main post-processing graph that we can have. So coming to the point, how the CST software is basically useful for the EMC simulation. So for many of the tasks that has been performed at the EMC stages, we have some of the multiple troubleshooting that has been coming. Like for the EMC simulation, for performing the EMC simulation, the cost and the simulation and the manufacturing has been much higher, and for the high efforts and the cost to be corrected, and there are some of the time delays in which the end product is being delayed for the final product output. So the EMC simulation by far as of now, the EMC simulation tool is giving you the access to reduce all these things. The first and the major upgrade for using any of the EM simulation software for EMI, EMC is you can have and go with the many n number of simulations, and you can have the multiple troubleshooting techniques before the final product has been created. So the before creation of the final product of the hardware part, you can go and troubleshoot your EMI, EMC stages. You can reduce the cost of your output your hardware, and you can also degrade the time for the final product creation. So basically, in the EMI EMC simulation in the design process, you can give the answer, what are the fundamentals, what if I can go with all these things, how the prototype has been done, what are the different type of prototype that you have designed, and what are the different parameters and the measurement that you are going to follow. So using the CST Studio for the EMC simulation can give you the accurate time, can give you the accuracy in the following three things. First one, you can have the simulation time. You can go with a number of possibility and perform many of the basic EMI EMC tasks with the simulation time. You can go with the modeling time, as you are saving the hardware cost of the final product for that's been verified for the EMI/EMC stage. And the next is the target accuracy. You are getting the accurate product before the final product has been manufactured. So for the model accuracy, you can always and trust the CST software for performing the EMI/EMC application. And for for the following results, we have the capability, and the CST software is much useful for giving you the EMI/EMC on many of the electronics components as well. If it's the PCB, if it's the connectors, if it's the cables, if it's the existing transistors, or many of the resistors are there, you can completely depend on the CST Studio Suite for performing the EMI/EMC task. So quickly, let me discuss the EMI/EMC application that's been dedicated into the electronics part. The first one is the emission, the different type of emission tests that we are going to conduct. And we are going to see the conducted emission. The next is the radiated emission. Some of the shielding efficiencies are there. Some of the emission that has been created from the cables that are carrying the digital signals. The next is the susceptibility. That's the main concept that been much used and widely used for now. And in the susceptibility, we are dealing with the electrostatic discharge analysis. The second one is the radiative immunity. Some of the bulk current injections are there. Some of the electric fast transient circuitry simulations are there. So these are the basic EMI/EMC applications for the electronics devices. And here you can see we have taken a basic example to explain you guys for the cascading simulation that can be possible using the CST Studio Suite. And here you can see the emission due to the common mode from the PCB that we have that is being given. Here in this structure, we have taken the two PCB that's been connected with each other with the help of cable. And we are assuming that cable is having the major part, as the cable is carrying the major part of the emission in the frequency range of 30 to 100 megahertz. So the emission is mainly due to the common modes on the cable that has been used. And all those common modes which is being generated by mode conversion on the PCB, we have to deal with that. And using the cascade model simulation, this entire model simulation can be performed using the CST Studio Suite. And in the schematic tab, we can do the simulation for this. And by doing this, we can have the exact emission that has been possible into the closed system, and we can detect the EMI/EMC standards, and we can perform the EMI/EMC test for this, and we can have the sort of correction that is being required before creating the hardware part. So by using this CST Studio Suite software, we are dealing with the simulation, which is not a big deal for the that can be creating the simulation in n number of parts, and with doing the simulation in parts and combining all those results, we can achieve this type of complex simulation for the EMI EMC testing. And this will save you on the cost. This will also give you the accurate result before the final product has been created. And for the for such environment, for many of the EMI EMC standards, you can deal with the many number of possibility and you can simulate the different type of environmental structures using the CST Studio Suite. So from here, we have done the co-simulation, and first we have done the simulation for the cable only. We have taken the 1 meter cable, and from both the ends we have given the excitation source. And as you can see, the S parameter graph plot is being plotted. And for the field probe, we have done the simulation for the two different operational frequency. We are considering the resonance at 140 megahertz. The second is the 280 megahertz, and the third one is the 420 megahertz. And here we have performed the simulation for the EMI EMC just only for the cables. And let me correct, it's just the single straight cable that we have used. We have not taken or we have not changed any of the different type of cables or the category. And we are just seeing the E field distribution by giving the 1 watt of the voltage, and for the 140 megahertz frequency, we are considering the E fields as well. So by the visualization in 3D, the end user can see what are the distortions that has been possible, at what specific points the distortion is been coming into the cables, and for different frequency and different resonance, we have given the simulation. And for the E field, that's we are again giving the 1 watt, and we have carried it for the 200 megahertz. And as you can visualize in this part, we are getting some distortion or the losses in the cable. So by this, the simulation can be possible in different number of parts. And as the CST software has many of the different availability of studios, we can perform the simulation in different parts as well. And the same thing, we have taken the next scenario in which we have taken the PCB in different parts. And as here you can see, we have these 3 different simulation that's individually been carried out. And then in the final one, we have created and combined all these 3 models with the one, and we have done the testing for the EMI EMC. So first one, as you can see, that's the symmetric circuitry that we have created in Symmetric Studio. The second one is the differential microstrip patch antenna that we have created and used the antenna maker software, which we have seen already in today's earlier session, in our today's session. And the third one is the connectors. The connector pins are available in the symmetric tab, and we have combined this as a single simulation project, and we have done the simulation. And as here in the cascading setup, we have this optimal case that we have discussed, and we have already considered the worst case. We have created the 2 scenarios, and for the 2 different objects and for the 2 different simulation, we have created the 3D blocks containing the field distributions as well. We have replicated in the worst case, we have replicated the same thing in the mirror form, in the mirror simulation, and we have combined this as the one entire simulation. And we have the graph plot for the S parameter versus the frequency, and with the worst case and the good optimal case for the simulation that's been performed onto the combined simulation, we can have the visibility and get the idea in the graph plot. The next scenario that we have already simulated in the CST software is bulk current injection. This is the BCI clamp in which we have created an environment in which the cable has been used, the straight cable has been used with the two end source for the feeding connection that has been given with the prop feeding, and between the two cable we have simulated and created the magnet. And with this type of simulation that can be possible into the CST, we can have the graph plot, and what are we can assume we can also do the simulation for the EMI EMC standards on how the magnetic effect has been affecting the cables as the cable is passing from the center of the magnet. Then the next same thing we have created for the bulk current injection, that's that we have designed with the PCB containing the filter off and the filter on simulation. So as you can see, the bulk current injection we have carried out for the PCB using the CST Designer PCB Studio, and we have attached the filter to this PCB, and we can compare the simulation results. As you can see, the filter off is there is much distortion that is been coming, and whenever you are turning the filter on, where the distortion is bit low. So these are the basic examples on the EMI EMC, and these are the basic examples which will be covered for the EMI EMC application using the CST using the CST Studio Suite. And as you can visualize in the graph plots, you can have the visibility of the current distribution. You can have the visibility of current distribution without the decaps, and with the decaps you can visualize this in 3D. The next is the enclosure simulation that we offer in the PCB Designer Studio. We have the capability to simulate the full PCB along with the enclosed models, like the PCB has been enclosed into the metallic casing, and how this different metallic casing will affect the PCB, and for the different application, for the different materials of the casing that has been defined, what are the signal losses that has been carried out in PCB can also be simulated. The next thing is the electromagnetic environmental effects that's been happening for the aircraft. As you can see, the visualization in this 3D visualization, the aircraft has been simulated into the CST Studio Suite software, and the environmental effects, or like the lightning strike effect on the aircraft, can also be possible. And you can visualize this. The red portion is the most affected area where the higher electric current has been get in contact with the lightning strike. So so for the CST Studio Suite, the CST Studio Suite is very much useful for the EMI EMC application, for the lightning strike as well, for the electromagnetic pulse simulation, for the high intensity radiated field also. We can also calculate the susceptibility of the cables along with the composite materials that we have. With the different material tabs, we can use these composite materials as well. So from here you can see we have simulated and created this CAD model of the aircraft that is being simulated into the CST software. And here we have given a lightning lightning feeding port that we have defined, and from this feeding port we have connected a cable, and that cable has been connected to the nose of the aircraft. And with this lightning channel effect, we have defined the probe for the higher impedance, and for the higher impedance, we have given this field source at the nose of the aircraft, and we will see how the light, if the lightning strikes on the aircraft, how and what are the effects that's been affecting the entire aircraft, and what are the main affected area. The next example that covers in E3 simulation for the EMI EMC application by the CST Studio is we have created a simulation project environment in which we have created entire facility with which we have this shielding that is being possible. So this facility has been created with HEMP shielding effect, where the radio waves, the RF radio waves has been blocked from the inner side. And with the use of many of the absorber materials and many of the absorbers, we have created this entire facility. We have created this building with the many of the materials, like the concrete one for the rebar we have used for the absorber one, and we have created this HEMP shielding effect. So inside this building, if the many of the end users are using the internet connectivity, the radio waves is not been crossing all this facility inside this building. So a cable has been laid out for the connection of the providing the broadband connection. So that shielding cable is also been simulated using the CST software, and we have also given the waveguide type of entry for the person to enter these facilities. So different type of shielding cables has also been possible, and for the creation of entire facilities as well, the CST tool has also been useful for performing all these EMI/EMC applications. And as you can see, the cable has been cable entry has been giving the susceptibility at 150 megahertz, and you can see the cable shielding that has been grounded with the PoE, the power over Ethernet EMP filtered has been on, and you can visualize the electric field that is being distributed from the cables. And by giving the 1 ohm of the shield to the ground resistance, no PoE filtering has been there. So you can have a better visualization in 3D formats as well. And the next thing is for the lightning strike on the aircraft. As we have created the lightning strike, we have the different type of antennas that has been simulated and created on the main aircraft. For the communication, we have this UHF antenna, many of the radar antennas are there, many of the GPS antennas are there, and all these antenna has been placed on the aircraft. And once the lightning strike has been given to this source, we can also visualize what are the effects of this high-end lightning source to all these electronic components. And here you can have the circuit simulation. In the circuit simulation, we can create the different type of antenna at the same time. We have this transmitting antenna, we have this receiving antenna, we can have the visualization of the GPS antenna, the combined antenna for the Wi-Fi communication, and we can simulate all those antenna into the single simulation run, and we can visualize the S parameter for the output and the calculation of all those results. So from here we have the graph where we can calculate the power loss along with the transmitting sensitivity and the received power along with the frequency. And here in the EMI margin, which has been calculated, which gives us the received power by giving the higher EMI range, the higher probability for the interference is there. So as you can see, there is an EMI margin that has been kept for the received power and for the transmitting sensitivity of the antennas as well. And the last is using the CST software in the single CST software into the single window. You can have all this task that has been performed. You can co-simulate many of the different structures. You can have the parametric view of the RF systems. You can use the violation metrics for getting you the perfect rule check for the PCB. And we have this navigation tree that is available to guide you and take all the different simulation projects that you have created. So this using the CST single CST simulation software tool, you can perform the many tasks, and at the same time with the different availability of CST Studio that we offer, and many of the different type of solvers that we can have. And for the simulation and measurement part, uh, we will see that in our next session in the afternoon one. Let me please uh, anyone from the organizing team, please come in. Hello, Dipti ma'am. Yeah, any member from the organizing team?
Yes, sir.
Yeah, is Dipti ma'am available?
I think it's busy at the moment.
Sorry.
I think within when the way for the moment.
Yeah, please. Hello, Dipti ma'am. Anyone from the organizing team, please come in.
Yes, sir. What? Sir?
Yeah, just as discussed for the morning session, I have completed from my side, and now we can have the lunch break. And after the lunch break, we will continue for the exploration of EMI EMC or using the CST Studio Suite. And here, I guess we have some of the questions from the participant. We will have the Q&A session for the participants as of now. Just for in the morning session we can have. So I quickly take the questions from the participant.
Okay, sir. Yeah, we can carry on with that.
Yeah. The first question is which application to be selected for the electronics package design modeling for micro millimeter wave application? So basically, we have in the CST, we have the different availability of solvers, and all those solvers are possible, are having the ability to give you the millimeter wave application scenario. And for the millimeter wave application, for the 5G application, for the 5G millimeter wave, the simulation, the antenna has to be verified for the main three concepts. For the 5G millimeter waves application, the first main challenge is the size, that the size of the antenna should be as low as possible. And in that compact size, we are going to have and deal with the transmitting and receiving antenna that's been placed near to the each other. So using the CST antenna array tool, we have this option to explore you and take you to the millimeter wave application designing as well. The next question is, sir, which tool and the solver can be used to study about the electromagnetic effects on transient phenomena like the lightning in CST? For the lightning effect in CST, I suggest you to go with the integral equation solver. As the lightning is an environmental effect, and for creating all those environmental effect into the EM simulation software, we are dealing with the higher electric field probe that is been connected with the cable on the aircraft or any of the ships as well. So lightning effect can be created with the help of integral equation solver, as all those heavily meshed structures are very electrically large in size. So for giving you the accurate and exact result with the simulation in lightning, I suggest you to go with the integral equation solver. The next question is, please, can you show how to define the composite material? For defining and creation of composite materials, we have some of the composite materials that are available in CST's component library. And if some of the composite materials are not available, I've already shown you how you can create your own custom design material with the material component with the option that is you can create the new material in the material library as well. In which the next question is, in which type of design we can use the waveguide port, discrete port, planar port, and the lumped element. Whenever you are giving some physical appearance for defining of the ports, you can definitely go with the discrete port, as you are giving some physical simulation, physical field that is being simulated into your antenna. For the waveguide port, we will definitely been given to a planar surface area. And for the lumped element, you can also use it for the simulation that can be possible for many of your applications. So in CST, we can have the option to give you and define many of the ports. As we have seen, we can go with the waveguide, or we can have the discrete, or we can have the planar wave, or we can go with the lumped elements as well. The next question is, can we simulate the RF circuit like the RF power amplifier, oscillator, mixtures in CST schematic? Yes, sir. Yes, we have this option to simulate the RF circuit, basically in the schematic tab, and in the CST design studio, we have all those options that are available. We have all those component libraries are also there, full of components. You can use all those components for creating your power amplifier and hairpin filters as well, using the CST schematic tab. The next question is, how much simulation time the software will take for the simulation of 10-meter twisted least cable bundle up to the say 2 gigahertz, and how much cores and memory will be required for this? This has to be taken by at the end of today's evening session. As we are in the evening session, we are going to see the simulation for the cables. So basically for working, basically we recommend that minimum hardware requirements are there. You can go with some of the minimum hardware requirements to run the CST software. We will, if any of the end users are requested, we will definitely provide you the detailed information about the main hardware that is being required to simulate all these heavily meshed created structures. The last question is, why different solver shows different S11 and pattern of the antenna? Which solver is the best for microstrips antenna simulation? Time of frequency domain. I guess the simulation of microstrip antenna can also be possible in two additional solver beyond time and frequency. I also simulated the microstrip antenna in integral also and asymptotic solvers also. So that doesn't depend according to the your application. The solver doesn't depend on what type of solver is being limited to your application. No, in CST you can change and you can go with the simulation of the available of the solvers that we have. But for giving you the accurate and best result, as you are much familiar, the microstrip patch antenna is a planar antenna which is having the single frequency operational, or it's having the multiple frequency operational. And as you have defined the field monitors into the simulation, we have gone through and taken the simulation for getting the results from S11, and for getting the gain pattern of your microstrip antenna, the time and frequency, both the solvers are best suited for your application. So here I have taken all the Q&A session from morning session. I guess we have now going for a lunch break, and from the organizing team, please come in.
Thank you, sir.
Yeah, Diptida. Yeah. Yes, ma'am.
Actually, I'm a student.
Yeah, okay, fine.
By this, we come to the end of the morning session. Afternoon session will start at sharp 2 p.m. So I request all the participants to be on the time. And thank you.
Yeah, sure.
afternoon all. Welcome back. Our afternoon session is going to start. Once again, I welcome Mr. Abhishek Dolakia to continue with the session. Thank you. Good afternoon. Sir, can we start? So Good afternoon, all. Welcome back. Our afternoon section is going to start. I welcome Mr. Abhishek Dolakia to take over the platform. Sir, please. Thank you.
Yeah, please acknowledge my screen. My voice is audible to the participant.
Yes, sir, it's audible.
Okay. Kindly acknowledge my screen is also visible.
Yes, sir, it's visible.
Yeah, okay. So I welcome all the participants again. In this afternoon session, we are going to see some of the basics of the EMI EMC using the CST Studio Suite software. And for the today's agenda, basically we are dealing with the electromagnetic simulations, the EMI EMC part. So here are some of the basic examples that CST tool is capable of. The first one is the current leakage that's been simulated around the Ethernet connectors that has been done from the CST perspective. The second one is the cylindrical scan of the radiated fields from the enclosure of a distance of 3 meters, 3 meter distance that has been having the EM fields. The third is the surface current distribution for the highly detailed model of the EST generators are there. And the next is the simulation carried out on the PCB layer structure. And the last is the coupling from an external Wi-Fi antenna that's having the shield of the cables. So from the cable shield, the field couples through the connector to an inner PCB. So these are some of the demo examples and electromagnetic simulations from the EMI perspective using the CST Studio Suite. And we start with our today's agenda. That's first we are going to see what are the basics of the EMI EMC. Then we will going to see the application covering the EMI EMC part. Then we will see what are the CST cable studio overview. And as I mentioned, the CST tool has the capability to simulate the cables, different type of cables. So we're going to see and design some of the cables using the cable studio. Then we'll see the EMI/EMC application on different cables, how the RF cable simulation can be possible with the Wi-Fi antenna. In the Wi-Fi antenna, the RF cable has been implanted, and how we are going to see the EMI/EMC effects on that. Then we will see some of the basics of the RF cables on automobile application covering the EMI/EMC part. And then after we will going to have some of the glimpse of EMI/EMC application covering the PCB design, and we are going to see the radiated emission on PCB for electronic devices. So basically, let's start with some of the basics and some of the news that we have received in the world from the EMI/EMC part, as the EMI/EMC has very much familiar is in the news, and due to some of the lightning strike on the wind farms and increasing height of turbulence, there is the rising number of lightning strike has been reported into the many of the aviation industry. So while physical blades damage is the most expensive thing, and the distribution caused by lightning, by far the most common is the damage to the control systems as well. So we will discuss what are the scopes of EMI/EMC, and as you all know, the ability of the electronic system to work with in its electromagnetic environment, and covering some of the influences without interfering of the surrounding devices that's we known as the emissions, and or being influenced by the surrounding equipments that's known as the susceptibility. And for the EMI compliance, as all the products are crucial enough, we have to deal with the susceptibility and emission as a well-regulated area in a well-regulated area. And for the kilohertz frequency range, if we are discussing for megahertz and for gigahertz, we are having some of the applications in all these frequency ranges like the switch power and the lightning, and that's covered in the kilohertz. And for in the megahertz, we are dealing with the EMP, the HIRF, and radio. And in the gigahertz, we are talking about the digital electronics and radar. So first we will discuss the EMI/EMC simulation in the design process. So what the design stage includes, as you all know, it accompanies the design process, and it can be used as an early stage for creating the environment. And it will also give the end user the fundamental questions and rights to ask the question, what if I do the simulation by this way? What if I can change some of the parameters? What if I can do the EMI/EMC in this environment? And using all this scenario and creating all this scenario, that can be possible in the CST Studio Suite. And as it can also deliver the output that's not been accessible by some of the physical hardware measurements. And you can always have the option to reduce the cost as the measurement or as the final product hardware measurement has to be created, and doing all those shieldings and cables on getting all those EMI/EMC losses reduced to the specific standard. You have to always modify all those measurements. So what are the troubleshooting that we can have? So we can help to understand the behavior of the device with the help of EM simulation software. And we will correct all those necessary requirements before the creation of the hardware, the final product hardware. So by doing all this stuff before creating the hardware, we are dealing with the no compare. We are not dealing with not a competitor to the measurement, but we should be used complementary parts for the doing the simulation one. As you can see on my screen, sorry for the delay. I got the connection loss from my PC. I just have to reconnect it. Yeah, any member from the organizing team, please provide me the sharing right. Yeah, thank you. Yeah, I guess the screen is now visible. Yeah. As I'm saying, these are the two main prototypes we have. On the left side, we can visualize the design final hardware product, and the same thing we have created in the 3D virtual prototype. We call it the 3D virtual prototype design, and we have some of the basic comparison as we have to deal with all the effects, including the manufacturing tolerances, and once on the hardware for checking for the EMI EMC applications. If this circuitry will be passed or failed, that can be decided after checking all the stages for the EMI EMC application. But in the 3D virtual prototype, we does not have to require to manufacture all these PCBs. We can all easily visualize the field in the 3D format, and we can get the exact idea at what location in the PCB we can have to do the shielding, and we can how we can reduce these losses. And the main advantage is we can easily parasitic, we can make some of the easy parasitic changes as I've discussed. If the hardware is being created and ready, and then after the EMC has to be performed, that hardware, the entire circuitry should be passed or failed. That depends on its standards and its output simulation on the output performance. But in the 3D prototype or in 3D virtual simulation like the CST software, we can easily get the idea on at what location we are getting all those distortion and losses, and we can recorrect all those things, and then after completing all those corrections, then after we can have the final we can design and go with the final prototype. That's always we know that's an pass that will pass the quality standards. So we have this an add-on advantage as compared to doing the EMI stuff on the real hardware. And we can have some of the information for getting the troubleshooting that's been done with the help of different solvers and different techniques as well. Yeah. The next thing is the EMC application on the electronic devices, as the first one is the emission and the second one is the susceptibility. So the emission deals with the conducted emission if it's the conducted emission. The second is the radiated emission. The third one is the shielding efficiency, and fourth one is, as you all know, the emission from the cables. And in the susceptibility part, we are dealing with the electrostatic discharge. We are dealing with the radiated immunity type. The third one is the electric fast transients, and the fourth one is the bulk current injectors. So in the PCB, if any of the end users are doing the EMI EMC stuff, they are just doing the rule check for the PCB. So basically a rule check is just getting all those standards verified by all those connections, and they are checking all the connectors and the connections are properly working or not. And in the EM simulation software, the rule checking for the PCB is must needed, because we are dealing and getting all those output simulation results with the base of the PCB that we are using for the EMI EMC application. So first and main concept for starting the EMI EMC on the CST software is we are dealing with the rule check basis. And as here you can see, we have an PCB which is having the DDR3 RAM, and many of the USB buses are there, and some of the SATA cables are there, and many of the pins are there that can be used. So first in the rule check, in the rule-based checking, first we are getting the power intensity graph. So that power intensity graph will show us the noise voltage that's been created from this PCB. The second one is the signal integrity. Then for the detection of the signal integrity, we are getting the we are seeing the eye diagram of the specific nanosecond time, and we are getting the eye diagram results for getting the signal integrity graphs. And then we are checking the EMI EMC limits, and for the emission spectrum, we are dealing with the electric field in dB watts with respect to the frequency in megahertz. Yeah. So next we will discuss about the workflow for the emission simulation. And for the first, we are dealing with the model geometry. How big is the model geometry, the dimensions. Then we are doing the 3D EM simulation task by creating and assigning the solvers and the meshing, defining the meshing and boundary conditions. Then we are creating the circuit setup. As you can here, you can see and visualize an entire symmetric circuit has been created. And then we are doing the circuit simulation for getting those emission simulation results. So this is the basic workflow for creating the emission simulation using the CST software. And here you can see we have created the emission from a DC-DC converter. We have taken the DC-DC converter and we have done the step-down bulk converter design using the CST software. And here I will demonstrate you how you can create this type of circuitry in the symmetric part. You just have to open the CST software. And from here, you can see there is the tab option available for the circuit and symmetric. You can go with the symmetric one. And here in the symmetric tab in the assembly, you can find all those details. And this is the main component device library. From here, you can find the device library of different components. And here you can see this device module library includes the diodes, some of the Z diodes, the Schottky diodes are there, some of the NPN BJT function, BJT amplifiers, PNP BJTs are there, and all the resistors, capacitors, inductors, chokes are there. So from here, we can have the simulation that can be possible. The other way is you can head towards the basic tab, open the basic tab into the CST software. And from here, you can have these blocks. You can create and visualize this block, and you can take this. And from here on the navigation tree, you can find the block section option is there. And from here, you can have the visibility and you can get the idea. You can have the circuit elements that is available. So here is the ground, here is the resistor, capacitor, inductors, many of the common modes are there. operational amplifier, mutual couplings are there. So these are some of the semiconductors. We have all the component library for you. We can also deal with some of the rectangular waveguides. We can also create the waveguides with the bands. We can have the E-plane obstacles, the H-plane opticals. You just have to manually drag and drop. And from the macros also, you can create some of the BJT filters, and many of the filter LC circuits are there. You just have to enter all these values. The return loss we are interested is 10 dB, and we press OK. And using the macros only, it will create the symmetric circuit for you. And as here you can visualize, all this circuit block has been automatically created. And you can have the values over here. You can have change the parameters and the values. Here are the values that you can have, and you can do the simulation. And from here, you can select as the block presentation, or you can have the task. You can assign this new task is there. And here in the task, you can have the three options. First one is the circuit one. In the circuit, you can have the S parameter, the operating point in DC, the AC combined result, the transient. We can have the mixers, the amplifiers, the I diagram analysis, and all those things. The second one is the generalized option, which will give you the flexibility to create some of the symmetric one with the building blocks, like you can create an array of an antenna. And at the same time, you can have to perform the symmetric of the matching circuit of the antenna. So that's the general part. And the third one is the simulation control, where you can sequence the simulation. You can perform some of the parametric sweeps are there. You can also do the optimization with the inbuilt optimizing tools that is available in CST. And the last one is you can combine all those some of the results for the post processing. So by this, in the schematic of the CST Studio Suite, we have created the DC to DC converter. And here, as you can see, this is the main source. This is the main switching loop, and we are having the load. And the same circuit with the same parameters we have created, we can convert this schematic circuit into the 3D layout format, as you can see here. And that the same 3D layout format has been compared with the designed final prototype, the hardware, and you can visualize and see the difference. So from here, from the DC to DC converter, we have done some of the modifications in it. And for the EMI rule check, we have done the layout modification. As you can see, this is the main original format. As you can see, the source line has been added to all those serial buses. Between all those serial buses, we have defined the lumped element ports. And we have done the excitation, and we are seeing the E-field distribution, the amplitude of the current distribution in the entire circuitry at 57 megahertz. And first, this is the main original modification. As you can see, the red is the much affected area for from the current source. As you can visualize the fields in the electric field. This is the original circuit, and once we have done some of the minor modification by just changing the source, by changing some of the assignment of the source, you can visualize the radiation in the lower PCB has been reduced and it has been gone. So just by doing some of the minor modification from your end using the CST Studio Suite, you can reduce all the EMI EMC losses at the beginning only. So this is the simple example for the radiated emission in the 3D simulation world. We have created the simple example I will show you. So in the radiated emission, we have this circuit simulation that's been targeted for giving us the transient signal integrity solution. And for that, we are considering the AC small signal analysis, by which we have combined some of the results. And in the system assembly modeling, as you can see, this in the system advanced assembly modeling. Just let me open that system assembly. From here, you can have the system assembly modeling tool that is available. And from in the main system assembly, you can create the assembly in the schematic one as well. And from here, you can just do the drag and drop. You just create all these things. You can ask for the NPN. You can change this device and connections also. Sorry for the connection loss. So as I'm saying, we are in the system assembly tab. As in the system assembly modeling, we have done this simulation. We have performed the simulation task, and we have created this series bus, and we have given the terminals. And once this type of symmetric circuit has been created by applying the external port and grounding and all those voltage, we are using and we are performing the E field distribution. As we are dealing with the prop values, we have defined the props, and we have done the simulation for the E field in the symmetric one. And you can have the combined result that has been plotted into a single graph. So from here, you can have the better visibility for the radiated emission in the 100 megawatt, under 100 megahertz. You can visualize there are not much of the radiated emission that's happening. Just this portion has been affected. As you can see, the red portion one. As we are going with the 350 megahertz, as you can see, much of the outer regions has been affected for the simulation. In the 3D EM simulation, you can see in 3D view. And for the 700 megahertz, you can see the main affected area is this serial bus. This is the much affected area at 700 megahertz. So by this example, you can get the better visibility for the radiated emission that has been performed using the CST Studio Suite. So now we are going to see what is the Cable Studio, and how the CST Cable Studio is a handy tool for creation of all those cables. How you can create and design some of the cables using the Cable Studio, and how we can perform the EMI EMC on those things. So now the first is we can analyze the complex cable bundles as we are dealing with the transmission line simulation or the crosstalk simulation or the EMI EMS analysis in the different 3D environment. We can also have the flexibility to have the simulation like the standard workflow using the time domain transient simulation and doing all those detailed analysis. And we can also have the field coupled workflow, that's the coupled transmission line along with many of the 3D environmental simulation. So we'll see how the Cable Studio is a useful tool in the studio for creating all those EMI stuff. So here you can see we have taken automotive car and here we have this 3D model with all the cable with all the cables that has been laid down on the automotive car. And here you can see the cable cross-sectional view. As you can see, and many of the end users know, there are a lot of cables laid down on the automotive car. And here you can see yeah. Any member from the organizing team, please come in. Can you please verify my PPT is visible and my voice is audible?
Yes, sir, it's visible and audible.
Okay. So now, as I'm saying, sorry for the interruption. As I'm saying, we can see what is the CST Cable Studio and how the CST Cable Studio is a very handy tool for getting you all the simulation that can be done on the cables. And using the CST Cable Studio, we can have the flexibility to have the analysis of all those complex cable bundles, all the single wire pairs, the twisted wire pairs, some of the many rigid cables are there, some of the coaxial cables are there, and all the simulation can be done with the adding of all those connectors into it, and we can have the create the 3D environments by which we can have the simulation for the crosstalk, or we can have the transmission line simulation that can be happening in the CST cables. We can have the flexibility to do the standard workflow simulation with the simulation and analysis part as well. And then we can also have the flexibility to use the field coupled workflow that's been simulated on some of the 3DM simulation environment along with the cables. So as here you can see, we have taken the full the 3D model of the automotive car, and as you all know, the automotive car has a lot of cables, and many of the cable harnesses has been there, and some of the cables are for carrying the signals. Some of them are used for the digital purpose, and some of them are used for the signal carrying from taking the interconnection between many of the environmental systems. The cable plays a very important role. So what we have taken, we have done the 3D model of the automotive car, and we have done the simulation on those automotive car, and we have laid down the cable inside that automotive car, and we have done the same thing in the symmetric one. And as you can see, we have performed the circuit simulation with the cable, and here you can get the cross-sectional view of the cable. And once the cable has been laid down on the automotive car, we have carried out the simulation that's been done. And for pin 1, we have shield the ground of the cable, and for the second simulation, we have done the shielding as an open one. And here you can see and visualize the fields that has been the current distribution fields that we can have. And we can get the idea and visualize all those 3D fields and how the cable simulation using those cables, the field distribution inside the automotive car has been affecting. So by this, in the EM simulation software, the Cable Studio is a much very useful tool. So from the machine workflow, we are starting with the cascading first. And for the cascading, if the cascading is applied onto a system that can be decoupled, first we have to import the CST project. We are doing the CST project analysis. That's the rule check for the PCB. Then in the next step, we are doing the complete transient CM voltage analysis using the schematic assemblies task. And then after we are going with the simulate the radiation from the cables in the real environment. That's the physical environment of the hardware. So let me explain with the basic workflow. We are starting and doing the workflow. As we are starting with the 2D transmission line modeling, we are using the CST Cable Studio for that. We are first defining and importing the 3D structure. Yeah, we are starting with the workflow for the 2D transmission line modeling, and for that we are we are using the CST Cable Studio. And for the first, we are defining and importing the 3D structure. Then we are done with once we are done with the modeling, we are setting up the 3D monitors for the cables, and then we are defining the cabling. We are defining the cabling for the cables, and then we are set up the parameters for the 2D environment generation. And then next we are using the schematic assembly tab, in which we can connect the appropriate circuitry to the cables. We are creating the environment for the cables to be laid down, and that can be connected with the different building blocks for the environment, for the creation of complete 3D environment structures. Then we are dealing with connecting the circuit elements with the cables. Then we are going to define the type of excitation that we are giving the simulation for the cables, and then we define the interaction with the 3D modeling. And once we have defined all those things, the final thing we are going to define is we have to define the props, which we can be easily done in the schematic system assembly schematic tab. And then after, we are choosing the co-simulation if any of the required is there. And then we set up the task for the creation of the transient or the AC simulation. So this is the basic workflow that we will follow using the CST Cable Studio. So this is the main graphical user interface for the Cable Studio. And as here you can see, this is the ribbon bar. That's the same as you have visualized in the CS Studio suite. This is the main drawing plane where you can draw the cables, where you can have the designing in 3D as well as in schematics also. The next is, this is the navigation tree, where you can have the cable navigation and all those content that is being required. Here is, you can visualize the cross-sectional view of the cables. The cross-sectional view is most needed for designing all those cables, and as many of the cables has been laid down near to each other, you can also visualize this cross-sectional view will be very helpful for the end user to get the idea what are if any of the cables has been interacting or intersecting with each other or not. And for easy stuff, we have the option for the end user to see the cross-sectional view of the cables as well. And then this is the message and the progress window. So this is the basics of the graphical user interface of the Cable Studio. In the cable ribbon bar, you can find all these options. We have the cable tabs, which has been very useful for creation of all those cables. Many of the cable harnesses are there. And for the editing of the cables, we have given some of the cable topologies, as many of the end users are interested in doing the cable topology, like the straight cable or connecting some of the junctions between the cables. That can be possible using the cable topology tab. The next option for the editing of cabling is the cable bundles. As you can see, we have the option to bundle many of the straight cables or different type of cables to a main bundle, and you can also have the connection between all those bundled cable topologies. Then we have the option for the connectors, as the cable needs to be connected to the different type of connectors at their end. So we have the library for the connectors. The next is the junction property, where we are dealing with the connection between the cables, and some of the junctions or the junction pin points about junction pins are there. We are have all those options. Then we have some of the curving modeling tools for the cables. If the end user is not much familiar and they have to create their own design cables, their own cable designs, they can use this designing tool like the curves, and buy all those many pattern curves or different curves. They can also simulate and create their own cables for their dedicated shapes. And the last is the pick operations. You can always pick any points of the cables and you can do the simulation part easily. So these are all the cable studios ribbon bar, which can be useful. And let me take you to the different type of cables which can be offered into the cable studio. The first one is the single wire, the straight single wire cable that we can do the simulation. The second one is the twisted cable pairs that we have for many of the operational, like the twisted cable has been used in many of the automotive industry and many of the different applications. The third one is the ribbon cables, which has the set of cables that's been laid out into a ribbon structure. The fourth one is the coaxial cables, where we have the coaxial cables that has been used, basic coaxial cables that we have used. And the last is the cable grouping that we can have. So we can also group the cables according to the user's convenience. Then we have the impedance calculator, which can be useful for calculation of all those impedance. And we can have some of the 2D transmission line modeling of the cables as well. So these are the main UI of the ribbon, cable ribbons options that we offer in our cable studio. The next thing is, if the end user is not much familiar with how to design the cables, then we have the option to import the cables from different vendors as well. Many of the different supported softwares also. We have all those import options available, from which we can also import the cables from the different softwares. And for those things, we have the harness description list, which will give you the idea, and from many of the public domain data format or data model in Excel scheme that's been used by OEMs and many of the suppliers. Not an issue. We support all the different type of import formats for importing the cables from different CAD tools, or many of the cable parts which can be used for the polygon lines, and many of the supported formats are also been there in our cable studio. We just have to import all those cables and go through with the attached harness simulation. The next thing is how the editing of the cabling can be done. So first of all, we have this cabling topology tool that is available. As I just said, we can have the cable topology from the curves. We can have the topology from the curves, or we can segment from the nodes. Basically, nodes is the main section of the cables which is being simulated into a smaller into the smaller environment. So we can have this cable topology option. The next is cable bundles, in which you can have the option to cable the bundles from the selected curves, or you can have the cable bundling from the selected nodes that you have created. And the third one is the cable bundle from which bundles from the start and end nodes. If you are dealing and interesting with the simulation of the cable bundles, you can go with the created nodes from their starting point and from their ending point as well. The next is the connectors, as I just mentioned, and the same is for the junctions. And the last is the cable properties, where we have these object properties and the material definition has been done. And in the cable studio, you can create and edit the cable bundles as we have just explained in this slide. So in the cable studio, the different type of cables that we have, as some of the basic categories I just explained, some of them are the single wire, some of the twisted cables are there, some of the ribbon cables are there, some of the coaxial cables are there, and the last is the cable grouping. So we have the different type of availability of cables in which we have the different options that is available into our component library. We will just see in the cable studio using the CST Studio Suite in the CST software in just few minutes. First, we will see we can have the access of the different type of cable library elements that we have available into our CST portfolio. Then we have all these supported cross-sectional type cables that we have the option, and then we have this cable grouping that's been done for the cables with the arbitrary cross-sectionals and many of the combining supported cross-sections also. So let me open the cable studio for you guys. And from here, you can have this cable navigation tool that is available. And here you can see the cable types are there. We have the different type of cables. We just double click on the single wire cables. And from here, we create the new cable. And we just enter the thickness and we press OK. And from here, you can see the cross-sectional view of that cable. And from here, we have this material library that is available. You can define the materials for the cables as well. And from the inbuilt component library, let me open the inbuilt component library for the cables. As we can also create the nodes for the following cables. We can import the cable harness as well. As I just mentioned, we have all the supportive import format that is available. And from here, we have the different options for the cables. And here we have this cable type. Yeah. And from here we have the preview for the different twisted cable pairs that is available. We can go with the simulation. We can create the new twisted cable pairs. You can get the idea how the cable, twisted cable will look in this cross-sectional view. Yeah, here it is. So from here, we have all these different libraries for the different cables that we offer. And here you can see we have this option available. And from here, you can have the preview of the different dimensions of the cables that we offer. So the dimensions of the cables are varying and different. And here you can see and preview the different type of single straight cables that is available into our component library. The next, we can have the simulation for the twisted cables. We can load from the library as well. And from here, you can visualize it. We have this preview for the ribbon cables. We have this different type of ribbon cables are there. You can visualize this in the cross-sectional view. You can change it as well. Then we have some of the cross-sectional cables. We have some of the cross-sectional cables that comes with the wire inside, that comes with the insulator inside, that the many have some of the screens as well, and some of the insulators that has been defined for the cables on the outer part as well. So you can have the cross-sectional view and you can just preview that here. And the last one is the cable groups. And from the cable groups, you can group the different type of cables, as here you can see visualize in 3D. We have this single twisted pair. We have grouped the cable for the twisted pair. Some of the single cables has been laid down the same way. We have the different component library for the cable dedicated for cables also. So by this, we have gone through some of the inbuilt component library of the cables. Then in the cables, we have this some of the options that are available. We have this some of the modeling option that is available. First one is the 2D transmit line modeling, the TL modeling, in which we can have the lumped element modeling, and then we can have the modal mode modelings as well. The next, as I mentioned, there is the impedance calculator, which will give and which will help you to have the values for the characteristic impedance for the calculation of propagation constant, some of the effective dielectric constant, some of the cable models, some of the voltage eigenvectors, some of the RLCG parameters, and the matching impedance networks as well. So these are the few of the options that we offer in the modeling of the cables. And as you can see in the cable navigation tree, you can find all this option. First one is the cable type, what type of cable that you have used. You can find the details of all those cables, what is the inner dimensions of all those cables that you have used from the component library. The second one is the material that you have defined for the cables. So what materials that you have defined for the specific cables, and any of the predefined materials can also be seen and available in the navigation. Yeah. Sorry for the delay. Yes. The next thing is the nodes that I am discussing. As you can see, we can create some of the small parts of the cables into the smaller section, and we can bend all those, get the connection between the nodes. So all those node information, you can have it here in the node tab. The next one is the segments, in which you can connect the two nodes and you can create the entire cable simulation into a proper segment, same way. The next is the cable bundles, where you can bundle or you can group the cables, and here you can see we have taken the cable cross-sectional bundle view, and from here you can have the cross-sectional view where the repeater wire is there, where the wire screen for one has been created, where is the outer sleeve, where is the inner sleeve, insulator part, the pin part, connectors are there. The next is what type of the main cable navigation tree, where you can find all those details. So now we will discuss some of the contents and how we can go with the workflow regarding the cable studio. So from here, we are starting with the new template, and from the new template, we are selecting the EMI EMC project portfolio, and into the EMI EMC project portfolio, you are selecting the radiated emission, and inside the radiated emission, you are selecting the cables for your simulation. And once you have done and you have done the simulation, you have selected this template for the cable studio, the best suited solver for your application has been defined. Now we have imported this 3D modeling of automotive car, as here you can see. And once the 3D modeling has been created, now we are heading towards the cable studio, where we can create and select the type of cable that we are interested in. And once the selection of the cable has been done, we can create the cable bundles, and we can lay down all the cable bundles into the specific location into the 3D model that we have created. And then we are dealing with the cable modeling, and we are calculating all those impedance losses, and the impedance calculator simulation has been done. And once this has been done, we are doing the circuit modeling in the symmetric pen. And in the schematic assembly tab, we are getting the prompts and defining all those ground sources and combining the simulation into the different environment. We are getting the final results, that is the 3D graph plot. In that's the 3D visualization of the fields on the 3D model that we have imported. So by this, this is the basic workflow how the many of the combined studios in the CST software can give you the accurate results on with the help of different type of cables on 3D models as well. The next thing is this 2D TL modeling section. Here in this 2D TL modeling setting, we have some of the options where we can select the signals from the cable modeling. So once we have selected the different type of signals from the different cable and selected cable models, we can add all those signals here. And after adding all those signals into the simulation part, we can do with the refresh and add selective signals into the NT. But we have to remove all the others from the main list. And once we have done the selection, we can remove the selected signals from the list, and we can also reset the highlight location in the drawing plane. So this is the one type of modeling tool that's been used for the cables in the 2D format only. And here in the next step, you can have the selection of the meshing. As you can see in the cables, we can also define the appropriate meshing. And here in the define extraction setting, as we are going to have the selection in meshing properties. We are giving the extraction setting where the search distance from the coupling of different cable bundles we have to enter, and the minimum sample length that we have to deal with. And the twisting accuracy, we can change it from high, normal, and low. And once we have done the simulation, we have selected the appropriate setting for the mesh. We can click here on the start meshing option is there. And once we have a small simulation has been carried out on the cable that we have laid down or selected, we can also visualize the meshing on those cables. The next and third option that is available in the 2D TL modeling setting is here in the modeling part. We can have to define the equivalent circuit of the cables. Then in the next option, we are dealing with the modeling settings where we have to deal with the ohmic loss, some of the dielectric losses in the cable, some of the LF reduction losses, and many of the options like we can go with the accuracy setting of the cable, and we can also select the signal type of unwanted signal that's been coming from the float cables, or we are using the ground cables as well. And we have to enter all these values. And once we are done with the simulation, we can export those model that can be exported into the 3D design model of the cables in the cable studio. The next thing is the impedance calculator. As you can see here, in the impedance calculator, we have these two settings that is available. The first one is the segment one, and in the segment section, you can have this segment list. You can have it packaging into the 3D format. The next is the relative position along with the segment, where you have to accurately lay the 2D or the 3D, lay the cable into the 2D or the 3D environment. And the third one is the signal and the sets to be defined, where you have to add defined signals, or you can rename or change the signal potentials, and you can calculate all those values. In the next setting of the impedance calculator, you can have the frequency SIP option, which will allow the end user to have the local frequency range. They can define the minimum frequency and maximum frequency for the cables. They can set the parameters for the logarithmic SIP options are there. Then they can also define the number of samples according to their needs. And once the model setting has been done, they can have the calculation for the ohmic losses or for the dielectric losses as well. And the next thing, the static solver, the accuracy of the static solver along with the twist accuracy, they can also add on using the settings that is available into the impedance calculator. The next thing that we are going to see is the circuit modeling aspect. And as here you can see, you can visualize the basic circuit that we have laid down. We have used the many type of node cables that's been used in the automotive industry, in the automotive car. And we start with the standard modeling. First, we have defined the transient task that we have needed. And from here, you can define the properties. And here in the property setting, you can have the simulation model that's available. So the two options are available for creating the simulation model. The first one is the standard model, and the second one is the dispersion model. So the basic difference between the standard and dispersion is that the transient task is been mainly recommended, and the S parameter simulation result can be possible. And in the dispersion model, if you are going with the dispersion model, the transient task can also be possible, and the AC and the S parameter is must needed. So this is the basic difference. The next thing is the field coupling workflow. As you can see in the schematic tab that's available into the assembly part, we have created a basic structure where we have done the simulation for the three same circuit, and we have defined the nodes between these three circuits. And once the coupling type we have to define in the simulation task, you can see the AC combined result option is there. You can select this in the simulation task, or you can define it into the new task option is there. Here you can have the AC combined result is being available. And for the coupling type, you can go with the unidirectional coupling that comes with the radiation or the irradiation, or you can also do the simulation in bidirectional coupling. So in the unidirectional, you can go with the AC and the transient task. Both things can be possible. But in bidirectional task, you can deal with the transient task only. So once in the simulation tab, you can select the AC combined result, and here in the cable field coupling, you can define the type of coupling, and here you can have these two options that's available. First one is the unidirectional radiation. The second one is unidirectional irradiation. The same way, whenever you are defining the simulation task in the transient one, the cable field properties, you can find the three options that are available. First one is bidirectional, and the both two are the unidirectional radiation and irradiation respectively. So the next thing that we are going to see is we have created an example in which you can get the idea how the Cable Studio has been useful tool for getting the EMI EMC on the cables. And for this, we have taken the scenario and created an environment in which we are dealing with an Wi-Fi antenna. That's the Wi-Fi router antenna that has been used, and that is been connected to the USB cable coupling. As you can see, the USB screened cable cross-sectional view here, and this is the main Wi-Fi router, and 1 meter cable has been connected to this Wi-Fi router. So we will see this experimental example that has been performed into the CST software. So as here you can see the Wi-Fi router that we are using. The Wi-Fi router has been is having the Wi-Fi antenna that's been placed onto the PCB structure that's designed on the PCB structure that has been laid inside the casing, the metal casing of the Wi-Fi router. So as here you can see there is the differential signal mismatch that's been happening between the cable and the Wi-Fi antenna that's been simulated into the PCB. So from here we have these different signals that we are getting by combining both these two systems. And from doing the simulation, you can get the idea by the cables, by using the different type of cables, we are getting this E-field distribution. And here you can see the losses that has been very much affected, and we are getting the field distribution graph plot at 2.4 gigahertz frequency that's been created onto a environment, into the 3D environment. And as you can see, the waves has been much affecting the connected part of the Wi-Fi router area as the cable is being laid down there also. So here you can see the radiation pattern. That's the radiation pattern, the gain plot of the Wi-Fi antenna that's been used and utilized. It's the far field result. From the far field result, you can see the Wi-Fi router has been giving us the omnidirectional realized gain. That's the gain pattern. And we are getting around 9.07 dBi value. That's the positive value in each of the directions. So as you can see, this spherical shape, that's the main coverage area of the Wi-Fi router that has been used. And as you can also notice, our 1 meter cable that has been connected to the Wi-Fi router, the half of the cable has also been affected with the radiation of the Wi-Fi router. So this also plays an important role on the cable simulation, and on those cables, all this external field is also playing a major important role in carrying all those signals. So the next thing is the PCB to the cable coupling. As you all know, we have this simulation being done into the CST studio, where we have some of the ferrite pens are there. Here you can visualize those ferrite pens are there. We have also taken some of the CM chokes are there, and some of the external pins and connectors has been used. So each of the system has been individually simulated, and in the schematic one, we can have the graph plot for the transmission waveforms. As here you can see this transmission graph plot. And once we have done the flexible shielding of the cables, we have received this transform wave at the specific point, where we have at the 500 megahertz, the pulse strings analysis has been done for the specific part as well. And as here you can see, there is no distortion that is available. And once we have done the flexible cable shielding, we are getting some of this losses, this distortion at the specific points as well. So using some of the choke magnets and ferrite pens, for the 500 megahertz frequency range, we have the pulse train that's been analyzed. And the next example, in which we have created the same environment of the Wi-Fi router that has been taken from the antenna maker software, and using those two Wi-Fi routers that's been placed at a specific location at a specific distance, we have laid down a 2 meter cable using the cable studio, and we can have the visualization of the cross-sectional view as this one cable is connecting these two Wi-Fi routers. So we can see what are the effects of this Wi-Fi antenna onto the RF cables and carrying all those signals has been distorted or not. So as we have done for the first router, we have doing the simulation for the first router as well. And for the USB cables, we are getting the graph plot in the current time signal versus the frequency plot. And here you can visualize this thing as the connecting cables are there, and we have taken the connectors and simulations along the cable. The first scenario, we have taken just one router and the same length of cable has been simulated. And we have visualized the CM current for the one router, and for after in the second scenario, in the second environment, we have added the second router at the end of the cable. So from here, we have compared a graph plot in which we are getting the current time signal in ampere per frequency range. And you can visualize these two difference. The green one is being simulated with the one router, and the red one is simulated with the two routers as well. So the practical scenario of the cable studio has also been there, and many of our client has been designed some of the hardware from the cables that has been designed using the cable studio in the CST software. We have this cable studio validation study that has been performed. And in this validation study, they have taken 4 differentiated cables that has been tested for the transfer impedance into the real life environment. And they have done the full connection setup, as here you can see and visualize them in the live hardware. And here you can see the twisted 2-pair couple cables has been used, and many of the single straight pair cable coupling has been used for their study. And the second thing, they have done the measurement and simulation result comparison between all those two things. And here, this is the main chamber of the box where they can have done the perform the simulation of the different cables that has been having the different nodes and simulations. And the measurement and the simulated result has also been compared. And here you can see the cable radiation that we are getting. So in the first scenario, they have done the simulation of the cables without the CM choke. And in the second one, they have done the simulation with the CM choke. So the emission from the PCB and the cable shield using the Gaussian pulse extraction that can be completely seen here in the electric field distribution plot. As here you can see and visualize the cables on the cables, how the signal is being flowing from 1 CM current from one circuitry to the second one. The next scenario in which the cable studio is much useful for the different type of cables and for many of the simulations is in the automotive industry. And for in the automotive industry, creating the EMI simulation along with the different type of cables and many of the twisted cables that can be done. Here you can find out the radiated susceptibility simulation that has been carried out. And here we have an antenna, that's the planar inverted F, that's the PIF antenna that has been used for the vehicle to vehicle communication into the automotive industry that has been used. And this antenna has been taken from the antenna maker software for the specific frequency, operational frequency. And once this antenna has been interconnected with the different type of cables, we can have the plot and do the simulation, and we can create the real world environment of the cables that has been laid on the real automotive car, and we can visualize the field distribution, how the antenna radiation and the cable emission field has been affecting the outer body of the automotive car. So this is the main basic example. I know this is a very heavily meshed cables. As here you can see, there are very many number of cables has been laid into the grouping of the cables. This is the live case environment and the case study taken from the automotive industry, and they are using this type of different type of cables and using the CST cable studio. And they have done this type of cable simulation, and they have properly meshed their structure. And on the electric field in the 3D environment, they are getting the best idea on what location and exact pinpoints, what are the distortions that has been happening from the cables as well. So the next cable project simulation that I have to discuss with you guys is the hybrid cable simulation that's been performed for the EMI facility. And this program has been switchable mode, which have the power supply driven at an sensor with high speed RS485 communication. So here are some of the sensors. We have this differential RS485 that's been playing a major role. The same way we have an SMPS that's been laid out, and the interference between the SMPS and RS485 circuitry has been connected with the different type of cables that we have. So from the SMPS the 4 different type of cables has been connected to the sensor load, and all this cable simulation has been done using the CST software. And you can see the grouping of the different type of cables, and you can also visualize what are the losses, how we can import the measured screen transfer impedance onto the cables as well. The next thing is the cable parametric extraction that we are going to discuss. And for the analysis of mutual capacitance between these two cables, we have to create a heavily meshed structure of the cables. And using the proper mesh structure, as here you can see on the edges as well, the meshing is been properly done. So as I mentioned in our morning session, the meshing plays an important role for giving you the best and accurate result from any EM simulation software tool. So as here you can visualize this, if all the type of tetrahedral meshing has been created on the cross-sectional view of the different grouping of the cables, and as this is a heavily meshed structure, it's giving you the best and accurate result by performing the solvers into solvers that are available into the CST software. The next industrial case study that we have taken is for the aerospace industry. In the aerospace industry, as you all know, the many type of different type of cables has also been used, and this is the same way, but in the next level step from the automotive industry, the aerospace industry is having a bit higher number of cables that's been laid down onto the structure, and many different type of cables has different role. And for the aircraft in the aerospace industry, as you can visualize, the different type of grouping of cables has been done onto this this helicopter, and this 3D CAD format 3D model has been inputted into the CST software, and then the different type of cable harness has been laid down, and the cable studio using the cable studio tool, the cabling of the simulation has been performed out. And here you can see for the simulation, for the live simulation, we have taken the help of antenna maker software, where we have used the aircraft communication antennas. This antenna has been properly patched. Then we have taken this antenna and done the simulation in the frequency domain solver, where we have created the the electric field distribution and all the simulation part. And The next, when the frequency domain solver, we are taking the near field source using the time domain solver and doing the cable harness. We are getting the E field distribution that has been performed onto the this aircraft, and as you can visualize the field distribution of the antenna that's been radiated, and you can get the better idea into the 3D format. The next real world environment is we have taken this windmill and for the wind inside the windmill the turbulence is there, and whenever this windmill turbulence system has been there, in the real world environment, whenever the lightning strike analysis has been done and carried out, in this windmill the different type of cables has also been used. Some of these cables are being used for the effectiveness, for the reduction of the effectiveness of the lightning strike onto the system. Some cables are used for the connection between the rotary motors and the wings and the blades. So in this environment also, the cable studio plays a very important role. And here you can also visualize the E-field distribution in the 3D format. The next thing that you can have to see, you can visualize is using the CST cable studio, how anyone can get the radiation capability or the susceptibility calculation from the cables. So first of all, we are dealing with the basic structure. We are taking this transmission line on the coaxial cables. First, we have this and single coaxial cable without having any additional reference conductor that has been modeled and added. So from the CST cable studio, these are the basic units that we have to select. We have to deal with the millimeters and megahertz frequency. And once we define the using the CST studio suite in the cable studio, first we have to define the trace. So basically the trace means the path where the small portion of the cable has to be defined. So we have to define the starting and the ending point and the dimension of the cables. So we have defined these two nodes of the cables from the starting point to the ending point along with its dimension. Then after defining the trace of the cable, we have to select the different type of cable that has been assigned to each nodes, and from the inbuilt available component library, we can take and change the different type of cables that is available in the component library of cables. And once you select the component of the cable, you can have the visualization in the cross-sectional view of the cable. And once the cable has been defined, we are now defining the inner coaxial cable type. We are dealing with the wire inner coaxial cable. Then we are defining the property, and then we are defining and assigning the property for the cables. As the three basic material properties has been assigned to this cable, we can also edit this material property, and we can change the epsilon value R, the epsilon value, the tangent delta value at the specific frequency along with its permeability. And in the next step, in the cable transmission impedance calculator, you can visualize the field distribution of the cables, covering the optical coverage range and the number of carriers that we have. What are the standard dimensions of the cables in millimeters that we have to offer? And here, from here, we have this graph plot for the magnitude versus frequency. And using this impedance calculator, you can get the idea at what specific magnitude and what specific frequency we are getting the exact data from the cables that we have selected. and then we have to follow some of the standard dimensions of the cable, as the inner dimensions are there, some of the standard dimensions are there, the number of start in one carrier that we have selected, the number of carriers, and the brain angle. The brain angle is the angle which carries the woes of the cables, and the optical coverage where we have to deal with some of the parameters as well. So once this thing has been this simulation task has been completed out, we have to carry the cable transmission equivalent circuit, and for creation of all those equivalent circuit, we are defining the ohmic loss and the dielectric loss as the main property. We just have to select the cables and define the modeling for those cables and calculating the ohmic loss and the dielectric loss. And then in the schematic tab, you can find this schematic logo that's been automatically created along with the cables. So this cable that we have created with the 4 connection pin has been created and made as a block element, and using this block element you can go and have the selection for the different type of grounding pins as there. And once this singular block element for the cable studio that we have created is been available into schematic one, you can just drag and drop all those components and create the co-simulation for those things. And from here, now we complete the symmetric property, and by creating the symmetric, we are giving the external port 1, we are defining the 50 ohm impedance, we are defining the ground plane, we are connecting both these two things in the cables, and again we are defining the 50 ohm impedance, 50 ohm resistors, and then connecting it to the short one. And then we have defined these 2 pin powers between these 2 points, and now we are manually changing and defining the connection losses. And in the simulation task, we have this AC combined result that we are much interested in. And after selection of the AC parametric list, we have to define the voltage at specific voltage, at what voltage we are interested in dealing the excitation of the parameters. And once we have defined the parametric options with the voltage, we are giving the maximum frequency, minimum frequency, and the number of step samples of the cables that we are going to simulate. And then in the pulse setting, we are defining the type of pulse and what type of source that you are using for the cables. We have to define that. We are taking the voltage as a source one. You can also go with the current source or the signal source according to your conveniency. And once this has been done, the last step is to define the boundary condition for the cables that we have defined. So in the boundary condition setting, we have the hexaedral meshing that's available. We are defining the type of meshing and its accuracy in the solver setting. And then we are defining the properly refinement of the mesh around the edges, as on the edges, the meshing should be properly meshed. The structure should be properly meshed, and for the well-meshed structure, it's give you the best and accurate results. And once this has been done, you can have the idea and you can visualize the surface current distribution on the cables, and you can have the idea of what are the radiation losses that has been happening into the cables. And you can visualize these things into the 3D format, into the electric field distribution, into the 3D graph plot.
Abhishek, you are muted. I think you have to unmute yourself.
Okay, sorry. From here, the summary is being there for the from the hybrid field cable couple simulation. We have performed the individual task and combine all those tasks into the same simulation environment. That's in the CST Studio Studio. So first in the 2D TL cable solver, we have defined and simulated the single cables and bunching and the grouping of the cables that has been done. Then we are dealing with the 3D full wave field source solver simulation, in which we have created a real world environment where we have taken and connected the two Wi-Fi routers, and we have connected both those two Wi-Fi routers with the cables, and we have created and done the simulation in the 3D environment. And then after we have this option and the capability to do the same task into the circuit solver, we in the schematic assembly one, we can perform the circuit simulation. And the same way, we can have this full bidirectional coupling between the cable and the real one environment can also be possible. And in the next, we have done the susceptibility and the emission analysis on the cables as well. And from the last, we have done the simulation for the workflow, where we have this radiated emission from the electronic circuit. And as the electronic circuit comes with the connectors and the cable, connector has been added to that. We have done the simulation. We can have the field distribution graph plot into the 3D formats as well. And this is the main last symmetric circuit that we are going to see for the today's session. And here you can get the better visibility and idea how the cable simulation has been performed onto the PCB. And you can visualize those 3D you can visualize the current distribution in the 3D format. And you can have it for the 1 megahertz frequency range. And you can have the better idea at what exact location on the PCB the main affected area has been covering, and all those area can be resolved and covered using the different type of shielding effects that you can do for the EMC applications. So here I conclude my today's session. From any member from the organizing team, please come in.
Thank you, sir. There are some questions in the chat box. Can we discuss it?
Yeah. Just one more thing I have to add. For the further communication, you can contact us. This is Abhishek P. Dolakia, myself, and you can note down my email ID that's displayed on the PDF on the PPT. And the second person is Mr. Parth Agrawal, sir. He is the technical director of Jyoti Electronics. You can also contact any of the person for any of the technical session or the technical regarding. You can also drop us an email, and any of the evolution license for the request of the evolution license or any of the purchase for the CST software, you can kindly drop us an email. We will definitely love to help you on those things. And for the further communication, you can drop me an email. And for the presentation slides, you can contact the organizing team. We'll definitely provide them this PPT for the audience to get a better idea about the CST software, and they can also explore the capabilities of software from their end also. So now here we take our Q&A session. we can start and have some of the questions that has been mentioned into the chat box.
So the first question is, it was observed that when we vary the frequency range, the mesh size also varies. For example, the simulation result of a component for a frequency range of 1 to 5 GHz is slightly different from the result when the same component is simulated for an extended range of 1 to 8 GHz. Is this obvious, or do we need to take care of it to avoid this variation in result?
For the variation in result, that always depend on the type of field monitors that you have defined. So as you are saying, the field results has been varying as you are taking from 1 to 5 gigahertz range, or you are considering the extended range of 1 to 8. That doesn't matter. The range is also there, but for taking the much higher range, that doesn't depend on what type of range that you are dealing with. That directly depends on what type of field monitors that you have defined. For suppose if I have defined the range from 1 gigahertz to 1 gigahertz to 3 gigahertz only for any of the planar patch antenna simulation, and I have defined more than 4 or 5 field monitors, that's obviously taking a bit longer simulation time, and the simulation result will also be taking a bit longer to be simulated. So it directly depends on what type of field monitors that you have defined, not on the range that you created.
Thank you, sir. The next question is there any toolkit for DDR compliance test? Is it possible to find the signal flight time through the trace for DDR4? If yes, is this including the wire flight time?
I'm not sure about the DDR compliance test, or I'm not having any of the idea regarding the signal flight time through the trace from the DDR4. But if you are interested in getting some of the EMI EMC simulation task on the PCB, we have the CST designer PCB, we have the CST PCB Designer Studio. I will drop you in documentation for the CST PCB Designer Studio. And in that, if the DDR4 compliance sheet or for the DDR compliance test can be possible using that PCB Designer Studio, you can definitely use this PCB Designer Studio using the CST.
Thank you, sir. The next question is, how can we model LITS cable?
For the LITS cable, we just have to define the parameters. The first thing is what type of cables that we are dealing with. If the LITS cable are the straight cables, we can go and do the simulation with the single straight cables. And for if the LITS cable are the twisted cable pairs, we can have the bundling of the cables for many of the grouping of the cables along with the nodes of the cables using the CST cable studio. And if the LITS cable is not available into the CST, you can also import the cables from the additional source, and you can perform the EMI EMC application on the cables as well.
Thank you, sir. The next question is there any demo workflow for conducted emission or radiated emission analysis?
Yes, there is a dedicated demo tool and tutorial videos are available, and some of our experts from Dassault system has taken some of the webinars on this specific topics for the EMI so as if any of the material has been required, like the webinar link or the webinar videos, I will definitely drop an email. Please drop me an email on the follow mention PPT. I will definitely share the webinar link. You can go through and learn some of the CE and RE analysis.
Thank you, sir. And next question is, in hybrid cable mode, is it possible to simulate Ethernet plus power lines?
in the hybrid cable mode, yes, we have this option, but I suggest to demonstrate and simulate the different type of cables like the Ethernet cable first into the cable studio, and then the next thing is the power line. The power line you can also do and simulate in the symmetric one. So once you can combine all those things, you can perform the bidirectional or unidirectional simulation task, as I will demonstrate it in today's presentation, and you can perform the simulation for the Ethernet plus power line cables as well.
Thank you, sir. The next question is it possible to simulate medical instrument with the help of your software?
Definitely, our software is widely used for the medical application, and here in the CST, as I mentioned in my morning session, the CST has wide range of voxel data family, and all those voxel data families using these voxel models, you can perform and create the medical instruments that is being required, and we have all those solvers that is also available for performing all those medical instrument simulation tasks as well. So yes, the CST is widely used in medical applications also.
Thank you, sir. One more question. Any inbuilt test setup model available for CRISPR standard radiated emission measurement?
Inbuilt setup, I guess I have that has been done by some of the Dassault system engineers, and in your many of the professionals from EMI, EMC standards, they have taken some of the webinars using this RE measurement simulation using the CIS PR standards, and all those inbuilt tools has been covered, but that is a bit lengthy process, and in this performing all the simulation tasks, it takes a it requires higher end configuration PC, and the simulation time is bit higher. So yes, the CST is able to give you the CIS-PR standard RE measurements as well.
Thank you, sir. Next question. How to do an air discharge ESD simulation in CSG?
Using the air discharge, I guess we have to define the simulation parameters for the air properties that is available in the material section of the component library. So we have also created the real world environment simulation, and for the air simulation discharge in ESD, we have the thermal and mechanical solver that is available into the CST software. So using the real world environment and doing all those discharge analysis, we have the dedicated tool for the spark reading that's been giving you the best accurate result for the RF breakdown with respect to air also.
Thank you, sir. The next question. Evaluation of EMI, EMC in IC design level layout. Will it support the software?
Yes, for the EMI-EMC application on the IC level design, if it's a IC or if it's the PCB or if it's single layer PCB or if it's multi-layer PCB, that all has been supported by the CST software.
Thank you, sir. The next question. Is there any model for vacuum relays?
For the vacuum relays, in the component library as of now, we doesn't have any of the models. But for the vacuum relay, I guess that's the option that is available from the static particle dynamic solver can easily and create the vacuum relays, and you can use the PIC domain solver for the creation of vacuum relays. But as of now, in the component library, we doesn't have any of the support for the vacuum relay.
Thank you, sir. The next question. Whether your software import from Cadence or Mentor Graphics PCB layout tool?
Yes, Manoj sir, we have the option for the import from the cadence and the meter graphic. And for the sake of conveniency, I will show you the supported formats that has been used into the CST software. As here you can see in the import export features, we have this 3D file format that is available. You can import the 3D CAD models from all these different type of softwares that supports the CATIA, ACIS, many of the SolidWorks, Solid Edge, some of the Parasolid, the Autodesk is there, the Siemens, and many of the 3D general file formats that also includes the step format, IGS, VDA, STL, OBG, and many of the different formats. And from different vendors and different softwares also, we have this wide range of import and export features that is available.
Thank you, sir. The last question in the chat box. Will CST support encrypted SPICE models?
Yes, in the CST symmetric tab and in the assembly tab also, you can have the option for the SPICE model importing. Just let me take you to that thing. And here in the block section, you can see the field simulators. You can have the CST suite for the PCB Studio. The Fast 3D blocks are there. And here in the data input, you can find this touchstrom format file block has also been supported. And here you can also import the SPICE block in the SPICE block models as well.
Thank you, sir. Is there any question from participant sides? Assume that there is no other questions from the participant side. So thank you, sir, for giving your valuable time. Before concluding, I request all the participants to switch on the camera to have a quick screenshot of our gathering.
One last question, ma'am, that has been received from
Yes, there is one more question.
Bhimrao Jadhav. Can you please read that question for me?
How to design N-type connector and SMA connector in CST?
In the CST, sir, for the designing of the connectors, I will take you to my morning session point. And at the time of demonstration in my antenna maker software, in the antenna maker software, you can have the option where you can have the simulation that's been possible for the connectors. And I guess I have used one of the import option from the antenna makers to the CST software for the SMA 50 ohm connector, I guess. So yes, using the antenna maker software, there are a lot of antenna connected templates that is being available. You can use them and you can have the simulation done into the CST.
Thank you, sir. I request once again the participants to please switch on their camera.
Yes, ma'am, I got all the questions.
Thank you. So, before concluding, there is a reminder. We are going to meet again on Monday at 4 p.m. to 6 p.m. with another two important personalities, Sri Vinicius and Sri Kantikumar Chikkam from Bosch India, Bangalore, on the topic EMC for safe, automated, electrified, and connected mobility. So I hope all of you will be there on Monday.
Let's just thank Abhishek Dwalake for sparing one full day. I hope all of us had examples of simulation studies of EMI EMC. Thank you, Abhishek, from the organizers. Thank you so much for your effort. Hope we can all come together tomorrow at 4 o'clock. Not tomorrow, day after tomorrow at 4 o'clock. Until then, thank you. Goodbye.
Yeah, I thank you all the participants, and I also much thankful to the organizing team for doing this wonderful webinar type of slots and giving us the opportunity to demonstrate our CST software tool for the EMI EMC capability. Thank you, ma'am. Thank you all the participants for joining. Have a nice day.